As each moment passes, the vastness of our universe continues to expand. Yet, the questions of what ignited the birth of this grand cosmos and what forces keep it bound together remain a mystery. Today, we embark on a journey to explore the enigma of dark matter and dark energy, two elusive, invisible forces that shape the very fabric of our reality, but remain largely beyond our comprehension. The most widely accepted explanation for the origins of our universe is the Big Bang Theory. According to this theory, the universe began as a singular, incredibly dense, and unimaginably hot point approximately 14 billion years ago. Picture it, a fully deflated balloon representing the entirety of the universe compressed into an infinitesimally tiny space. Then, in an instant, this tiny speck exploded, not as a traditional explosion, but rather as a rapid expansion. This moment marked the birth of all that we know, with everything suddenly stretching outward into the vast expanse of space. As the universe began to expand, it also began to cool, allowing the first elementary particles to form. The temperatures dropped, and these particles began to combine, giving birth to the simplest of elements, hydrogen and helium. Over eons, these building blocks clumped together due to the force of gravity, forming vast clouds that would later give rise to the stars and galaxies that populate our cosmos today. The universe's journey was one of continuous expansion and cooling, leading to the formation of increasingly complex structures. This theory is not just a story, it is supported by a series of scientific observations. One of the most critical pieces of evidence is the cosmic microwave background radiation, a faint glow that permeates the universe, a relic from the early universe that has survived through the ages. This radiation is a direct result of the heat from the primordial state of the universe, now stretched and cooled as the cosmos expanded. Further backing the Big Bang Theory is the observation that galaxies appear to be moving away from us in all directions, suggesting that the universe is still in a state of expansion. This discovery aligns with the expectation that space itself originated from an extraordinarily dense point and has been spreading outward ever since. In a way, the expansion of the universe is akin to the surface of a balloon inflating, with galaxies marking the surface as it stretches and grows. The continuing expansion serves as a real-time testament to the theory's accuracy, providing a framework to not only understand the universe's birth, but also its ongoing evolution. There are several critical pieces of evidence supporting the Big Bang Theory. First, the observation of galaxies moving away from us in all directions provides compelling proof that the universe is expanding. This motion directly correlates with the notion that space itself began as an incredibly dense point, and over time, it has been stretching, causing galaxies to recede from one another. Another key observation is the cosmic microwave background radiation. This radiation is almost uniform across the sky, representing the afterglow of the universe's hot and dense initial state. It provides a snapshot of the universe when it was just a few 100,000 years old, offering a glimpse into the early moments following the Big Bang. The abundance of light elements, such as hydrogen and helium, in the universe also lends weight to the Big Bang Theory. These elements were formed during the early stages of the universe in a process called nucleosynthesis. In this process, the cooling of the universe allowed the formation of these simple atoms in the first few minutes after the explosion. This collection of light elements can still be observed today, scattered across the cosmos. The large-scale structure of the universe, the distribution of galaxies and galaxy clusters, further supports the Big Bang Theory. The way matter clumped together to form galaxies over billions of years can be accurately modeled by computer simulations that take the Big Bang as their foundation. These simulations help us visualize how the universe's structure developed over time, providing a clear picture of the forces at play during the universe's evolution. In the early moments after the Big Bang, the universe was a radically different place from what we experience today. It was a furnace of unimaginable heat and density, filled with a chaotic soup of energy and fundamental particles. Picture a region of space packed with so much heat that even the most basic forms of matter could not hold together. During this fiery phase, the universe consisted primarily of elementary particles, protons, neutrons, and electrons, along with an ocean of energy. These particles couldn't combine to form atoms because the overwhelming energy kept them moving too quickly, causing them to constantly collide. This rapid movement of particles also meant that light could not travel freely. Instead, it was constantly absorbed and re-emitted by the energetic particles, trapped in an opaque cosmic fog. As the universe expanded, it began to cool, and this cooling allowed the particles to lose some of their energy. Eventually, this allowed the formation of the simplest elements, mainly hydrogen and helium. This was a crucial step in the universe's evolution, as it laid the groundwork for the creation of the first atoms. For several minutes after the Big Bang, the universe remained in a state of turmoil, with radiation flooding every corner. It wasn't until about 300,000 years later that the conditions finally stabilized enough to allow light to travel freely. This marked a pivotal moment in cosmic history. The universe became transparent, and photons, the particles of light, could finally move freely across the cosmos. This moment also marked the creation of the cosmic microwave background radiation, the afterglow of the Big Bang. This faint, uniform radiation gives us a snapshot of the universe at a time when it was just a few 100,000 years old, providing an invaluable glimpse into the infancy of the cosmos. Scientists have developed several methods to estimate the age of the universe, each offering a piece of the puzzle. Central to these calculations is the concept of cosmic expansion. Imagine the universe as a balloon slowly inflating. As the balloon expands, galaxies, the points on the balloon's surface, move farther apart. By studying how quickly galaxies are receding from us, scientists can reverse the expansion and trace it back to the point when everything was concentrated in a singularity. This moment, the Big Bang, is when the universe began its journey of expansion. One of the critical tools scientists use to study this expansion is redshift. When light from distant galaxies travels toward us, it shifts toward the red end of the spectrum. This shift tells us how fast those galaxies are moving away, and by extension, how long ago the Big Bang must have occurred. The greater the redshift, the farther away and faster the galaxy is moving, providing a timeline of cosmic history. Another important method involves studying the oldest known stars. By analyzing the light emitted by these ancient stars and examining their chemical composition, astronomers can estimate their age. This, in turn, offers clues about when stars began to form in the wake of the Big Bang. The oldest stars we know of help define a cosmic timeline, providing researchers with a valuable framework for understanding the universe's early history. Each of these methods, from redshift to stellar age estimation, builds a robust picture of the universe's origins, helping scientists refine their understanding of when and how the cosmos began and evolved. Through these interconnected observations, we are slowly piecing together the intricate, beautiful story of the universe, its birth, its ongoing expansion, and the mysteries that still lie beyond the horizon. The cosmic microwave background radiation is an essential element in our understanding of the universe's origins. This faint glow, which permeates the entire universe, is a relic from the intense heat of the Big Bang. By studying its minute variations, scientists can derive invaluable information about the conditions that existed in the early universe. These detailed analyses help refine our estimates of the universe's age, which has been narrowed down to approximately 132 billion years. This figure has been arrived at through a combination of diverse research methods, each contributing a unique perspective to the overall picture. By integrating data from various scientific approaches, a more comprehensive timeline of the cosmos emerges. It is through the synergy of these different methods that we are gradually uncovering the profound mysteries of the universe's beginnings. The Big Bang Theory stands as the most widely accepted explanation for the creation of the universe. However, several alternative theories present alternative views that challenge, expand upon, or offer different interpretations of the origins of the cosmos. One of the most thought-provoking of these is the steady-state theory. This theory proposes that the universe has always existed as it is today, in an eternal, unchanging state. According to this concept, new matter is continuously created to fill the void left by galaxies moving away from one another. In this scenario, the universe remains infinite, both in time and in space, offering a stark contrast to the dynamic and ever-evolving model suggested by the Big Bang Theory. Another alternative model is the cyclic universe theory. This suggests that the universe goes through endless cycles of expansion and contraction. After each Big Bang, the universe expands, only to slow down and eventually collapse back in on itself in a process known as the Big Crunch. This collapse is followed by another explosive event, a new Big Bang, marking the start of another cycle. Thus, time is viewed not as a linear progression, but as a repeating, cyclical process, creating a loop of birth, death, and rebirth on a cosmic scale. In addition to these, the multiverse theory offers a mind-bending possibility that our universe is merely one of many in existence, each with its own distinct origins. In this framework, different universes may have come into being through a variety of processes, including random fluctuations in energy. As a result, each universe could have its own set of physical laws and structures, leading to a vast diversity of realities. Some proponents of this theory even suggest that our universe could have started as a small patch within a far larger cosmic landscape, eventually giving rise to multiple distinct realities, each with its unique characteristics. These alternative theories expand our imagination and challenge our fundamental understanding of existence itself. While the Big Bang Theory continues to dominate the scientific discourse, exploring these alternatives encourages a broader perspective on the universe's origins and emphasizes the complexity of its cosmic beginnings. Among the greatest mysteries of the universe is dark matter. This elusive substance constitutes a significant portion of the universe's total mass, yet it remains invisible to current detection methods. Imagine attempting to build a structure with invisible bricks. Although the bricks can't be seen, their weight and placement have a massive impact on the stability and function of the building. Similarly, dark matter doesn't emit light or energy, rendering it invisible to even the most advanced instruments. Despite this, its presence is inferred from its gravitational effects on galaxies and other cosmic structures. Scientists first detected dark matter's influence when they observed that galaxies were rotating much faster than expected. According to the laws of physics, if only the visible matter within these galaxies were present, their fast rotation would cause them to disintegrate. But this doesn't happen. Instead, galaxies remain intact, suggesting there is an unseen mass, dark matter, that provides the additional gravitational pull necessary to hold them together. Dark matter is a subject of intense research, driven by its puzzling nature. Despite extensive studies and indirect evidence confirming its existence, we still do not know what dark matter is made of. Several theories abound, proposing that it consists of unknown particles that do not interact with light or ordinary matter, making them almost impossible to detect. Some even suggest that dark matter may consist of exotic forms of matter that challenge the very laws of physics as we understand them. The enigma of dark matter continues to fuel scientific curiosity, with researchers exploring a variety of experimental and observational approaches to uncover its true nature. Beyond its mysterious composition, dark matter plays a pivotal role in shaping the structure and behavior of galaxies. It acts like an invisible scaffolding, providing the gravitational foundation upon which galaxies are built. Regular matter, such as stars, gas, and planets, is not sufficient to explain the movements and behaviors of galaxies. For example, scientists have noticed that stars located at the outer edges of galaxies move much faster than they should, based solely on the mass of visible matter. This discrepancy points to the presence of unseen mass, exerting an extra gravitational influence. This unseen mass is thought to be dark matter. Furthermore, dark matter affects how galaxies interact with one another. When two galaxies come close enough, their dark matter halos can produce intricate gravitational interactions, sometimes leading to spectacular mergers. These collisions often trigger the formation of new stars, altering the galaxy's structure and appearance. In this sense, dark matter is more than just a passive force. It is an active, unseen architect, guiding the evolution and stability of galaxies across the cosmos. As we delve deeper into the cosmic landscape, dark matter remains one of the biggest unsolved puzzles of modern science. While we cannot directly observe it, We know it must be there due to its gravitational effects on galaxies and other large-scale cosmic structures. The leading hypotheses surrounding dark matter's composition are varied. One prominent theory posits that it is made up of weakly interacting massive particles, or WIMPs. These particles are thought to be quite large and interact very weakly with regular matter, which makes them nearly impossible to detect by traditional means. If these particles exist, they would cluster around galaxies, contributing to the gravitational forces that hold them together. Another possibility is that dark matter could consist of axions, which are hypothetical, ultra-light particles that also interact very weakly with regular matter. Some researchers are drawn to this idea because axions could also help explain certain puzzling observations in particle physics, such as those related to high-energy interactions. Additionally, some scientists speculate that dark matter might be composed of primordial black holes, tiny black holes that could have formed in the very early universe, right after the Big Bang. These black holes would differ from the typical ones we observe today, which form from the remnants of dead stars. Primordial black holes could vary in size, and their existence might account for some of the gravitational phenomena we see without requiring the introduction of new particles. In the search for answers, some researchers have also begun to explore modified theories of gravity as an alternative to dark matter. These theories propose that the behavior of galaxies and galaxy clusters might not require dark matter at all, but rather a revision of our understanding of gravitational forces. As technology and observational techniques advance, scientists continue to test each of these hypotheses, hoping to uncover definitive evidence of dark matter's true nature. Detecting dark matter is one of the greatest challenges in modern astronomy and physics. Since it does not emit light or energy that we can observe directly, scientists have had to develop innovative ways to study its presence. One of the most effective methods involves studying the rotation of galaxies. By measuring the speed at which stars rotate within a galaxy, scientists can calculate the amount of mass required to hold the galaxy together. If only visible matter were present, galaxies should rotate much more slowly. However, their observed rotation speeds suggest that an additional, invisible mass, likely dark matter, is exerting gravitational influence. Another technique used to study dark matter involves galaxy clusters. These clusters contain far more mass than can be accounted for by visible matter alone. By measuring the gravitational lensing effect of light passing near these clusters, scientists can infer the presence and distribution of dark matter. As light from distant objects bends around the cluster, it provides valuable clues about the total mass within the cluster, including the dark matter that cannot be seen. Through these methods and others, scientists continue to push the boundaries of our knowledge, inching ever closer to uncovering the elusive nature of dark matter and its role in shaping the universe. Scientists analyze the cosmic microwave background, a remnant of the Big Bang's afterglow. The subtle temperature fluctuations within this ancient light offer profound insights into the universe's early stages. These temperature variations map out the distribution of matter, including the elusive dark matter. Despite being invisible to our instruments, dark matter's presence becomes evident when combined with other observations. These temperature fluctuations provide clues, helping researchers craft a picture that suggests the existence of dark matter. This mysterious substance, which constitutes a large part of the universe's mass, remains invisible but undeniable in its influence. By employing advanced observational techniques, scientists create maps that outline dark matter's role in shaping the universe. While it cannot be directly observed, dark matter's gravitational effects ripple through the cosmos. It plays a pivotal role in galaxy formation and structure, binding stars and galaxies together. But its true nature remains one of the great unsolved mysteries in astrophysics. Around the world, researchers are conducting a variety of experiments to uncover the secrets of dark matter. One key method involves placing ultra-sensitive detectors deep underground. These detectors are shielded from cosmic radiation and other interference, aiming to detect the rare moments when dark matter particles interact with ordinary matter. In laboratories, scientists recreate conditions that could allow dark matter particles to collide with atomic nuclei. By analyzing the resulting energy and patterns, they hope to identify clear signs of dark matter's presence. Another critical approach involves observing the universe on a grand scale. Massive telescopes are dedicated to studying the movement of galaxies and the shape of galaxy clusters. One fascinating phenomenon, known as gravitational lensing, occurs when light from distant galaxies bends as it passes near massive clusters. This bending allows astronomers to map out dark matter's distribution indirectly, revealing how it impacts the structure of the universe, even though it remains invisible. Space missions that measure the cosmic microwave background radiation also contribute valuable data. This faint afterglow from the Big Bang holds critical information about the early universe, providing hints about dark matter's influence during cosmic formation. Meanwhile, particle colliders experiment by smashing particles together at high speeds, searching for new, heavier particles that could potentially be candidates for dark matter. All these methods, though distinct, work together to bring us closer to unraveling the mysteries of dark matter. They offer a glimpse into the hidden but powerful force that governs the cosmos in ways we're just beginning to understand. The quest to understand dark energy began in the late 20th century. While studying distant supernovae, massive explosions marking the end of a star's life, astronomers observed something extraordinary. Supernovae, which serve as beacons for measuring distances in the universe, showed unexpected dimming in their light. Based on the expected expansion of the universe, scientists had anticipated the light from these supernovae to fade in a specific, predictable way. But the data suggested otherwise. The distant supernovae were dimmer than expected, indicating that the universe wasn't just expanding, but expanding at an accelerating rate. This discovery led to the proposal of dark energy, a mysterious force believed to be responsible for the accelerating expansion of the universe. Although its exact nature remains unknown, dark energy is thought to make up a significant portion of the universe's total energy content. It works like a form of energy that fills space, exerting a negative pressure that drives galaxies apart, accelerating the expansion of the universe. This discovery has profound implications for understanding the fate of the cosmos. If dark energy continues to dominate, it suggests a future scenario known as the Big Freeze. In this scenario, the universe will continue expanding indefinitely, causing galaxies to drift further apart. As the stars burn out over billions of years, the universe will grow colder and darker. The realization of dark energy not only transformed our understanding of cosmic expansion, but also raised essential questions about the ultimate destiny of the universe. Dark matter and dark energy are two of the most intriguing and elusive components of our universe. While dark matter is a form of invisible mass that shapes the structure of the universe, dark energy is a repulsive force driving its accelerated expansion. These two forces work in opposition to one another, with dark matter binding galaxies together, while dark energy stretches the universe apart. To understand dark energy, imagine blowing up a balloon. As air fills it, the rubber stretches and the surface expands outward. In the same way, the universe is expanding, but instead of air, dark energy exerts a constant push that accelerates this expansion. After the Big Bang, gravity initially slowed the universe's expansion, but about 5 billion years ago, observations revealed a surprising shift. The expansion began to accelerate. This shift indicated the presence of dark energy, a powerful force that counteracts the gravitational pull of matter. Unlike ordinary matter, which clumps together and exerts a gravitational pull, dark energy seems to be spread evenly across the entire universe. It triggers a repulsive effect, pushing galaxies apart, counteracting gravity's pull, and accelerating the expansion. This repulsive force works in tandem with dark matter, which contributes to the structure of the universe by providing mass and gravity. Dark energy is thought to make up roughly 70% of the total energy content of the universe. Despite its vast influence, dark energy remains an enigma. While scientists can observe its effects on cosmic expansion, its true nature remains hidden. Understanding dark energy is critical for understanding not only how the universe expands, but also what the future holds for the cosmos. If dark energy continues to dominate, it could lead to a future where galaxies drift apart, stars burn out, and the universe gradually grows darker. The challenge for scientists lies in the invisibility of dark energy. Unlike visible objects, dark energy does not emit or reflect light, making it impossible to observe directly with telescopes. Instead, its existence is inferred through indirect observations, such as the light from distant supernovae and the cosmic microwave background radiation. These observations suggest that the universe's expansion is accelerating, but they do not provide direct insight into the true nature of dark energy itself. Despite these challenges, dark energy is one of the most significant forces in our universe, shaping its expansion and determining its ultimate fate. Researchers continue to explore this mystery, hoping to unlock the secrets of the force that drives the cosmos ever outward, reshaping our understanding of the universe's past, present, and future. The enigma of dark energy stands as one of the most perplexing and captivating puzzles in modern astrophysics. Comprising about 70% of the universe, its influence is vast, yet its true nature remains largely elusive. As scientists continue to explore this cosmic force, it becomes increasingly clear that the existing framework of fundamental physics, shaped by the theories of gravity formulated by Isaac Newton and Albert Einstein, does not adequately account for the phenomenon of dark energy. The quest to reconcile dark energy with these well-established theories presents an intellectual challenge, one that forces researchers to reconsider how gravity and the very fabric of space-time operate on a cosmic scale. At the core of this challenge is the tension between dark energy's accelerating effect on the expansion of the universe and the gravitational models that have stood the test of centuries. The situation is complicated by the sheer scale of the universe itself, an almost incomprehensible expanse that stretches across unimaginable distances and spans eons of time. To study dark energy, researchers must analyze data gathered from distant galaxies, often from billions of light years away, and over epochs of time that stretch far beyond human experience. These immense distances introduce significant uncertainty into measurements, compounding the difficulty of isolating dark energy's effects from the myriad of other variables at play in the cosmos. As scientists study the universe's most distant structures, its galaxies, clusters, and cosmic voids, they encounter countless unknowns, each of which can influence their conclusions. Isolating dark energy from the complex web of gravitational forces, matter distributions, and other cosmic phenomena is no simple task. Moreover, the field is filled with a variety of competing theories, each offering a different interpretation of what dark energy might be. On one side, there are ideas such as the cosmological constant, a concept introduced by Albert Einstein, which suggests that dark energy is a fundamental property of space itself, inherent in the very structure of the universe. On the other hand, more dynamic models propose that dark energy evolves over time, changing in strength and character as the universe ages. This diversity of perspectives only adds layers of complexity to the scientific endeavor, as each theory requires rigorous testing, validation, and refinement. The stakes of this investigation are nothing short of monumental. Dark energy may hold the key to understanding the ultimate fate of the universe, whether it will continue expanding forever, eventually slowing down and collapsing back in on itself, or reach a state of stasis. Such revelations would not only shift our understanding of cosmic evolution, but could provoke a profound rethinking of humanity's place in the universe. Philosophical and scientific discussions would undoubtedly arise, touching on deep questions about existence, the nature of time, and the very meaning of life itself. If we can begin to grasp the true nature of dark energy, it could reshape the trajectory of human knowledge in ways we have yet to fully imagine. Moreover, uncovering the secrets of dark energy could inspire advancements in technology and new methods of exploration, pushing the boundaries of what we know and how we explore the cosmos. With a deeper understanding of how dark energy operates, we might develop innovative ways to observe distant galaxies, gather data on cosmic phenomena, and test theories in ways that were previously unthinkable. These new techniques could lead to groundbreaking discoveries, expanding our knowledge of the universe in unexpected directions. Ultimately, solving the mystery of dark energy is not merely an academic pursuit. It is a quest that could profoundly alter our perception of reality, shifting the very framework within which we understand the world and our place in it. Dark energy's impact extends beyond science, reaching into philosophy, technology, and even our collective future. As we strive to comprehend the universe more deeply, the discoveries we make about dark energy may lead to a more profound connection with the cosmos, offering new perspectives on existence and the future of our species. It could become the catalyst for a new era of exploration, discovery, and technological innovation, an era in which humanity begins to understand the true scale and nature of the universe. The mysteries of dark energy are not isolated from other cosmic phenomena. One such mystery is the black hole, a region in space where gravity is so intense that not even light can escape. This strange and fascinating object forms when a massive star exhausts its nuclear fuel and can no longer sustain its own weight. The resulting collapse of the star's core creates an incredibly dense region of space, where gravity becomes so powerful that it warps space-time itself. This collapse often results in a dramatic explosion known as a supernova that expels the outer layers of the star, leaving behind a dense core that continues to collapse into a singularity. The boundary surrounding this black hole, known as the event horizon, represents the point of no return. Once something crosses the event horizon, it is drawn inexorably toward the singularity at the center of the black hole, a region where gravity is thought to become infinite. The event horizon itself holds crucial importance in both observational astronomy and theoretical physics. For anything that crosses this boundary, no information can escape, rendering it invisible to outside observers. This makes the study of black holes, and the event horizon in particular, a tantalizing mystery for scientists, one that could provide profound insights into the nature of gravity, space-time, and the universe's fundamental laws. Interestingly, black holes come in a variety of sizes, from stellar black holes, which are formed when individual stars collapse, to supermassive black holes found at the centers of galaxies. These supermassive black holes can have masses millions or even billions of times that of our sun. The formation of these immense objects is still a subject of intense research, with theories suggesting that they may arise from the merging of smaller black holes or the collapse of massive gas clouds in the early universe. Regardless of their origin, black holes continue to represent one of the universe's most extreme environments, where the laws of physics break down in fascinating ways. In parallel to the study of black holes, researchers also investigate the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation provides a snapshot of the universe just a few 100,000 years after its formation, offering crucial insights into the conditions that existed at that time. The study of the cosmic microwave background allows scientists to test cosmological models and make predictions about the structure of the universe. By analyzing this radiation, researchers can reconstruct a picture of the universe's infancy, helping us understand how galaxies, stars, and other cosmic structures formed. The cosmic microwave background also carries crucial information about the distribution of matter in the early universe, including density fluctuations that eventually led to the formation of galaxies and large-scale cosmic structures. By studying these fluctuations, scientists can refine their understanding of the universe's expansion and evolution, shedding light on the nature of dark matter and dark energy. In this sense, the cosmic microwave background is a window into the past, a relic of the universe's earliest moments that continues to offer insights into the forces that shape the cosmos as we know it. In conclusion, the pursuit of understanding dark energy represents a journey into the deepest questions of the universe. As we continue to explore this enigmatic force, we are not only uncovering the secrets of the cosmos, but also pushing the boundaries of human knowledge. With each new discovery, we come closer to answering some of the most profound questions of existence, reshaping our understanding of space, time, and the very fabric of reality itself. Cosmologists study the universe on the largest scales, seeking to uncover its intricate structure and the forces that shape it. One of the key areas of research lies in the cosmic microwave background radiation, CMB, a faint glow left over from the Big Bang. This radiation provides crucial insights into the early universe, but different cosmological models predict varying amounts and patterns of this radiation. When scientists compare their observations of the CMB with predictions made by these models, they can assess which theories hold up under scrutiny. Discrepancies between expected and observed data often lead to revisions of existing models or, in some cases, prompt entirely new theories. In essence, the CMB acts as a cosmic messenger, revealing secrets about the very fabric of the universe. It helps refine our understanding of fundamental concepts such as dark matter, dark energy, and the rate of cosmic expansion. This radiation is not just a relic from the past, it is a central piece in the puzzle of understanding the universe's history and its potential future. The universe, when viewed on a grand scale, appears as a vast and complex tapestry of structures, a masterpiece of cosmic engineering. At its largest levels, it takes the form of a vast web, intricately woven from galaxies and clusters of galaxies. These clusters are not scattered randomly across the cosmos. Instead, they are grouped together in a manner that suggests a larger design, forming an elaborate pattern through vast stretches of emptiness known as cosmic voids. Some of these voids are so enormous that they can span billions of light years, containing few, if any, galaxies. The galaxies themselves tend to cluster together, with some clusters containing hundreds, if not thousands, of galaxies, all held together by the force of gravity. Beyond these clusters, there are even larger structures known as superclusters, vast conglomerations of several galaxy clusters, all interconnected by massive filaments of dark matter, a mysterious and invisible substance that does not emit light but plays a pivotal role in shaping the universe's gravitational structure. Dark matter, though unseen, has an undeniable influence. It impacts the movement of galaxies and clusters, helping to bind them together. Its gravitational pull provides the framework for how matter behaves on the grand scale, creating the conditions for galaxies to form, move, and interact. However, it is the cosmic filaments that form the backbone of this structure. These immense thread-like formations, stretching across the universe, guide the flow of matter through space. Like the strands of a spider's web, they stretch over vast distances, weaving through the cosmos. These filaments are composed not only of galaxies, but also of dark matter and gas, with their gravitational pull creating the conditions for stars and galaxies to form along their length. They represent the largest known scale of cosmic organization, dictating the flow and distribution of matter. At the intersections of these cosmic filaments sit galaxy clusters, massive gatherings of galaxies bound together by gravity. These clusters, along with the dark matter filaments that connect them, create a massive cosmic network. The formation of these filaments and clusters is an ongoing process that has spanned billions of years. Over time, gravity has pulled gas and dark matter into these threads, leading to the creation of stars and galaxies. Some of these filaments can stretch for millions of light years, while others are smaller in scale. This vast cosmic web, known as the cosmic web, outlines the large-scale structure of the universe, revealing how galaxies and clusters are interconnected across 3 dimensions. As we zoom out from individual clusters and filaments, we encounter the vast cosmic voids, expanses of space that contain very few galaxies. These voids are not merely empty spaces, but integral components of the universe's large-scale structure. They are the gaps between galaxies, clusters, and superclusters, providing a stark contrast to the dense regions filled with matter. These voids can span billions of light years across and serve as a reminder of the contrast between the empty spaces and the rich, densely packed clusters that fill the rest of the universe. The expansion of the universe adds another layer of complexity to this grand structure. The discovery that galaxies are moving away from each other, with the fabric of space itself stretching over time, has been one of the most intriguing revelations of modern cosmology. As the universe expands, the distance between distant galaxies increases, and the very fabric of space stretches to accommodate this growth. This phenomenon, first observed in the early 20th century, has since become one of the cornerstones of our understanding of the universe. The large-scale structure of the universe is a remarkable interplay of dense clusters and vast emptiness, held together by the threads of gravity that bind galaxies, clusters, and voids into a unified cosmic web. Among the most fascinating aspects of the universe's large-scale structure are the cosmic filaments, enormous strands of galaxies and dark matter that stretch across space. These filaments are the largest known structures in the universe and form the backbone of the cosmic web. Their role is crucial in the formation and distribution of matter. Gravity pulls matter into these filaments, creating stars, galaxies, and clusters. These filaments serve as highways for the flow of matter, guiding the creation and evolution of cosmic structures over billions of years. The cosmic filaments also illustrate how galaxies are not scattered randomly throughout the universe, but are organized in intricate patterns. Galaxies tend to cluster together in groups, forming large structures known as galaxy clusters. These clusters are often part of even larger structures called superclusters, which stretch across vast distances. Between these clusters and superclusters, there are vast regions of space known as cosmic voids. These voids are the emptiest areas in the universe, containing very few galaxies and highlighting the contrast between the densely packed clusters and the vast empty spaces that separate them. The large-scale organization of galaxies is a result of the gravitational forces that have acted on matter since the early universe. The conditions present in the early universe set the stage for this cosmic arrangement, with gravity shaping the motion and distribution of galaxies over billions of years. As we study this arrangement, we learn more about the universe's evolution, including how matter clumped together after the Big Bang, and how galaxies moved and interacted over time. This cosmic layout also provides important clues about dark matter and dark energy, two enigmatic substances that influence the structure and evolution of the universe. The formation and evolution of galaxy clusters are among the greatest mysteries in cosmology. These clusters, which can contain hundreds or even thousands of galaxies, provide insight into the universe's larger processes. At the core of each cluster lies a massive collection of galaxies bound together by gravity. Surrounding these galaxies is hot gas and dark matter, creating a complex and dynamic environment. Scientists believe that the earliest fluctuations in density in the universe led to the formation of these clusters, though the exact mechanisms remain unclear. One of the most intriguing aspects of galaxy clusters is the role of dark matter in their formation. Although dark matter cannot be seen directly, its presence is inferred through its gravitational effects on visible matter. Dark matter makes up a significant portion of the universe, yet its exact nature remains elusive. Understanding how dark matter interacts with visible matter in galaxy clusters could reveal critical information about the universe's structure and evolution. Over billions of years, galaxy clusters undergo significant changes. They may merge with other clusters, leading to the formation of even larger structures. These mergers release vast amounts of energy, observable as shocks in the hot gas surrounding the galaxies. Scientists are keen to understand how often these mergers occur and what impact they have on the evolution of galaxies within the clusters. Each discovery in this area brings us one step closer to understanding the true nature of the universe and the mysterious forces that govern its evolution. The distribution of galaxies within clusters presents one of the most enigmatic puzzles in the study of the cosmos. Some galaxies spin rapidly, while others appear to be moving toward the center of their respective clusters, as though drawn by an invisible force. This apparent diversity within galaxy clusters raises crucial questions about the histories of individual galaxies and the environmental factors that may shape their formation and evolution. What is it that determines the varied motion of these galaxies? And how have the interactions within their clusters over time influenced their current state? Research continues to probe into the profound role of cosmic events such as supernovae and the shock waves they generate. Supernova explosions send out massive bursts of energy and can significantly alter the gas surrounding galaxy clusters. These cosmic detonations impact the temperature and density of the gas, which in turn can influence the growth and behavior of galaxies. By examining these phenomena, scientists are inching closer to uncovering the intricate processes that guide the formation of galaxies within clusters. These studies are a vital piece in unraveling the vast and complex history of the universe itself. Through cutting-edge telescopes and advanced simulations, scientists work tirelessly to decode the mysteries of galaxy clusters. As they continue to explore these complex structures, they edge ever closer to unveiling the deep truths about the universe's formation and its ongoing evolution. Understanding the very structure of the universe is essential for answering many of the grand cosmological questions that lie before us. It is through the lens of these celestial systems that we seek to comprehend the cosmos on a grander scale. Imagine the universe as a vast, interconnected web, where each strand represents a galaxy or a galaxy cluster. The way these strands interlace directs the flow of cosmic matter and energy across the fabric of space. Studying this cosmic web provides the keys to understanding the fundamental rules that govern the universe. One of the most significant questions in cosmology concerns the origins of the universe itself. The distribution of galaxies offers vital clues about the earliest moments after the Big Bang, shedding light on the processes that set the stage for the universe's expansion. By tracing the patterns found in these cosmic structures, researchers can step back in time to explore how the universe evolved over billions of years. This investigation also ties into the deeper mysteries of dark matter and dark energy, two elusive forces that exert a profound influence on the universe's behavior. Dark matter, though invisible, acts like the glue holding galaxies together, while dark energy is responsible for driving the accelerated expansion of the universe. Mapping the interactions of visible matter with these unseen forces allows scientists to gain a deeper understanding of their true nature and their role in maintaining the delicate balance of the universe's energy. These insights not only enrich our knowledge of the universe, but also guide us in refining models of cosmic evolution. These models are pivotal in forecasting the universe's future. Will the universe continue its endless expansion, or will gravity eventually cause it to collapse in on itself? Each of these possibilities offers profound implications for our understanding of the cosmos, guiding our conception of the past, present, and potential futures. The structure of the universe thus becomes a cosmic map, pointing the way forward as scientists embark on their journey of discovery. By piecing together the complexities of the universe's framework, they not only seek answers to questions about its formation and evolution, but also grapple with larger existential inquiries about our place within this ever-changing and boundless cosmos. Time, as scientists define it in the context of the universe, is an essential measure of change, the continuous progression of events that shapes all of existence. To understand time in this vast sense, one can think of it as a flowing river, a steady current marking every moment that contributes to the cosmic narrative. This river encompasses everything, from the smallest particles to the grandest movements of galaxies. However, time in the universe is not merely a relentless ticking of a clock. Instead, it is deeply tied to the interactions of objects in space, and this relationship plays a critical role in our understanding of the cosmos. For instance, when a star explodes in a supernova, the precise timing of the event provides invaluable insight into the star's life cycle and the energy it releases into the universe. Time, therefore, serves as a framework for understanding the evolution of the universe, whether it is the formation of planets, the movements of celestial bodies, or the orbit of satellites. The theories of physics have radically transformed how we perceive time. Albert Einstein, for instance, revolutionized our understanding by linking time with space in his theory of relativity. According to Einstein, time is not an absolute, unchanging entity. Rather, it is intrinsically tied to the fabric of space and can stretch or contract depending on the gravitational forces at play and the speed of an object. At speeds close to the speed of light, time behaves very differently from how we experience it in our everyday lives. This concept of space-time, where time and space are inseparable, demonstrates that time is not an unyielding constant. Rather, it is a dynamic quantity shaped by the universe's underlying forces. This concept has profound implications for how we interpret the passage of time, especially in the context of the universe's grand scale. Scientists use time as an indispensable tool for decoding the behavior and changes of celestial bodies, helping to shed light on the mysteries of existence and the unfolding story of the cosmos. For many years, the notion that time might not be linear, or that it might be an illusion, has captured the imaginations of scientists and philosophers alike. One of the most compelling theories arises from the framework of relativity, which suggests that time and space are intricately interwoven. In this view, time can vary depending on the speed of an object or its proximity to massive gravitational sources. For instance, an object traveling at high speed or near a black hole experiences time differently than one that is at rest or far from gravitational influences. This challenges our conventional understanding of time as a consistent and unchanging phenomenon. Quantum mechanics, on the other hand, introduces even further complexities. At the subatomic level, the behavior of particles often defies the expected flow of time. In some interpretations, events may even appear to occur out of sequence, suggesting that the fabric of time itself is more intricate than we realize. Adding yet another layer of complexity, the philosophical argument of eternalism posits that past, present, and future exist simultaneously. In this view, time is not a moving line from past to present to future, but rather a vast landscape in which all moments exist as one. This radically shifts our understanding of time, suggesting that the events we experience are merely our perception of a much more tangled, multidimensional reality. These theories, ranging from relativity to quantum mechanics and eternalism, present time as a far more complex and mysterious force than we traditionally imagine. As scientists continue to explore the fabric of time and its relationship with the universe, they push the boundaries of our understanding, questioning the very nature of existence itself. The idea of time travel, which has long been a staple of science fiction, finds its roots in the serious study of modern physics. At the heart of time travel lies Einstein's theory of relativity, which shows that time is not a fixed, unchanging entity, but something that can bend and stretch based on speed and gravity. For example, astronauts on a fast-moving journey through space, or those living at high altitudes, experience time slightly differently than those on Earth. Their clocks tick slower, a phenomenon known as time dilation. Moreover, the idea of traveling backward in time raises even more intriguing possibilities. Some scientists have theorized about hypothetical time loops, similar to a wormhole, that could potentially allow a person to travel to an earlier point in time. If such a passageway were discovered, it might enable someone to revisit moments from their past. However, this concept is fraught with complexities and paradoxes, such as the infamous grandfather paradox, which asks what would happen if someone were to alter a significant event in their past, thereby potentially altering the present. In addition to relativity, quantum mechanics introduces another layer of complexity to the discussion. Some interpretations of quantum theory suggest the possibility of parallel universes or alternate timelines. In such a framework, it may be possible to travel to a different timeline without creating the contradictions that arise in traditional time travel scenarios. While the concept of time travel remains speculative, it continues to inspire scientific inquiry and captivates our imaginations, urging us to explore the unknown frontiers of physics. Time is not merely a backdrop against which the events of the universe unfold. It is a fundamental aspect of the cosmos, shaping the very behavior of matter and energy. In both everyday life and in the study of the universe, time helps us understand motion, change, and the connections between distant events. By analyzing how objects move and interact over time, scientists can gain insight into everything from the movement of planets to the behavior of subatomic particles. In physics, time provides the framework for measuring the intervals between events. When we calculate speed, for instance, we relate distance to time, understanding how long it takes for an object to travel a given distance. This relationship between time and motion is essential for studying change in the universe. Time is the measure that enables us to connect the seemingly disparate phenomena of motion and transformation, bridging the gap between the vast movements of galaxies and the fleeting behavior of particles in the quantum world. Time holds an undeniable and essential place in the fabric of the universe, profoundly shaping our understanding of space, gravity, and the very nature of reality. In the theory of relativity, time is not seen as an isolated concept. Instead, it is intricately intertwined with the three dimensions of space to form what we now call space-time. This merging of time and space fundamentally alters our comprehension of both. Time, in this context, becomes a flexible entity rather than a fixed and unchanging constant. Under the influence of gravity, time's flow is subject to change, especially near massive objects like planets and stars. The stronger the gravitational pull, the slower time appears to pass relative to areas with less gravitational influence. For example, someone near a massive celestial body would experience time moving more slowly than someone situated far away from such a mass. This phenomenon is not merely theoretical, it is an observable reality that shows how deeply time is influenced by the forces at work in the universe. It reveals a dynamic rather than static nature of time, one that shifts depending on location and context. When stepping into the microscopic world of quantum physics, time takes on an even more curious role. At the quantum level, events unfold in ways that defy our classical understanding. Particles behave in unpredictable, sometimes seemingly random manners, their interactions governed by probabilities rather than certainties. Over time, scientists have developed models to explain these behaviors, and the study of how particles evolve with time has provided critical insights into the fundamental rules that govern their actions. Thus, time is not merely a passive observer of events, but an active participant in shaping how the universe functions at its most basic level. Time, in essence, is not just a unit of measurement. It is integral to the very way we experience and interpret everything around us, from the ticking of a clock in our daily lives to the vast, sweeping events unfolding across the cosmos. Time is woven into the fabric of reality, influencing the motions and interactions of every particle, star, and galaxy. As physics continues to evolve, so too does our understanding of time, leading to new ways of thinking about its true nature. Recent developments in theoretical physics have led to profound shifts in how we view time. For centuries, time was considered a steady, linear progression, a constant flow from the past to the future. However, newer theories challenge this simplistic view, proposing that time may not always operate in a straightforward manner. One of the most intriguing revelations comes from the study of quantum mechanics. At the quantum level, particles often appear to exist in multiple states simultaneously, in what is known as superposition. This challenges the conventional understanding of time as a linear sequence of events, suggesting that time might be more flexible, with the possibility of multiple outcomes unfolding at once. Moreover, Albert Einstein's theory of relativity offers a radically different perspective on the relationship between time and the universe. According to relativity, time is not universal. It can run faster or slower depending on the speed at which an observer is moving or the strength of gravity in their surroundings. The closer one is to a massive object, like a planet or a star, the slower time moves relative to regions where gravity is weaker. This observation further complicates our understanding of time, showing it to be deeply influenced by the very structure of space-time itself. Additionally, the theory of relativity hints at the possibility that time might not be an isolated phenomenon, but part of a larger, more complex framework. In this view, time is interconnected with space in ways that we are only beginning to understand. This interwoven nature of time and space suggests that our conventional understanding of time may be far too simplistic. As we explore the deeper layers of the universe, we may need to revise our fundamental assumptions about what time is and how it works. The study of time, particularly in extreme conditions, raises fundamental questions about its very existence. Is time an illusion? Can time be reversed? What happens to time near black holes, where gravity is so intense that it warps the fabric of space-time? Each new discovery about time pushes the boundaries of our knowledge, inviting us to rethink not only the nature of time itself, but also our place in the vast, mysterious universe. One of the most captivating mysteries in modern cosmology is dark flow, a phenomenon that suggests a force beyond our current understanding is influencing the motion of galaxy clusters. Picture the universe as a vast ocean, with galaxies drifting like boats, generally moving in accordance with the universe's expansion. However, dark flow reveals that some galaxy clusters are behaving differently. These clusters appear to be moving in a specific direction, as if they are being pulled by an unseen force, one that cannot be explained by the known gravitational effects of nearby structures. The first hints of dark flow came from the study of the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. By examining tiny temperature fluctuations in this ancient light, scientists noticed something curious. Certain galaxy clusters seem to be moving toward a particular point in the sky. specifically toward the direction of the constellations Centaurus and Hydra. This motion did not align with the gravitational forces of known cosmic structures and suggested that some unknown force might be at work. This discovery opened up a new area of research, raising the possibility that there are unseen regions of mass, possibly located beyond the observable universe, that are exerting a pull on galaxy clusters. The implications of dark flow are profound. If this phenomenon is real, it could point to the existence of massive structures that lie beyond the observable universe, structures that we cannot yet detect with our current instruments. These distant entities might be exerting forces that affect the motion of galaxy clusters, reshaping our understanding of the universe on the largest scales. Dark flow presents an exciting puzzle that challenges scientists to think beyond the limits of our current knowledge, pushing the boundaries of what we know about the cosmos. The evidence for dark flow comes from two main sources: the movement of galaxy clusters and the cosmic microwave background. By tracking the motions of these clusters, scientists have observed a pattern. Certain clusters appear to be moving in a direction that cannot be explained by known gravitational influences. This coordinated motion suggests that something larger, perhaps an unseen mass or structure, is pulling on the galaxies. Furthermore, the study of the CMB reveals subtle variations in temperature across the sky, fluctuations that could be caused by the influence of unknown structures. Together, these observations support the idea that dark flow may be the result of gravitational forces exerted by unseen masses far beyond the edge of the observable universe. While the evidence is compelling, it does not provide a definitive answer. Some researchers propose that the observed movements of galaxy clusters could be due to local gravitational effects or the influence of known structures, like galaxy superclusters. Dark flow remains a subject of ongoing research and debate, with scientists working tirelessly to uncover the true cause of this mysterious cosmic behavior. As more data is collected and analyzed, the mystery of dark flow may one day be solved, leading to a deeper understanding of the forces at play in the universe. The concept of dark flow challenges our assumptions about the universe's structure. If dark flow exists, it suggests that the universe is not as uniform as we once thought. The standard cosmological model, which assumes that the universe is homogeneous and isotropic on large scales, might need to be revised. Dark flow could be evidence of vast unseen structures influencing the motion of galaxies over unimaginable distances. These structures might be remnants of a past universe, or they could represent a larger, more complex framework in which our universe is situated. One intriguing hypothesis proposes that dark flow is the result of gravitational interactions with massive objects located outside our observable universe. These objects might be part of a larger multiverse, with other regions of space interacting with our own in ways that we cannot yet perceive. Alternatively, dark flow could be the consequence of the gravitational pull of superclusters or other massive structures that lie at the edges of the known universe. Such massive entities could be shaping the motion of galaxies in ways that we are only beginning to understand. The potential role of dark energy and dark flow adds another layer of complexity. Dark energy, the mysterious force believed to be driving the accelerated expansion of the universe, could be playing a part in this cosmic drift. While dark energy typically causes galaxies to move apart, its influence on galaxy clusters could be more intricate than previously thought. The interplay between dark energy and dark flow is an exciting area of research, one that could reveal new aspects of the universe's expansion and the forces that govern it. As scientists continue to probe the depths of the cosmos, the mystery of dark flow remains an enticing enigma. Whether it is the result of unseen cosmic structures, the influence of dark energy, or some entirely unknown force, dark flow represents a profound challenge to our understanding of the universe. With each new discovery, researchers are getting closer to unraveling the secrets of this strange phenomenon, which could ultimately lead to groundbreaking insights into the nature of space, time, and the fundamental forces of the universe. The possibility of dark flow reshaping our understanding of the universe is a tantalizing idea that has captivated the curiosity of scientists for years. Dark flow, refers to a peculiar movement of galaxy clusters, seemingly pulled by a mysterious force, one that defies conventional explanations rooted in observable physics. If these galaxy clusters are indeed being dragged by something beyond our universe's observable limits, it could challenge everything we think we know about the fabric of space itself. This raises profound questions about the very nature of space, its expansion, and the hidden forces that might be at play on a cosmic scale. It could even force us to reconsider the foundation of dark energy, the elusive force believed to be accelerating the expansion of the universe. Such discoveries have the potential to radically alter the course of theoretical physics. They could lead to a redefinition of how we view the universe's history and its evolution. No longer would we see galaxies as isolated islands scattered across the vast void. Instead, they might be revealed as intricate components of a far-reaching cosmic web, connected in ways that are only beginning to be understood. This realization could open up an entirely new frontier in astrophysics, one that calls for a shift in our fundamental understanding of how the universe functions and evolves. However, resolving the mystery of dark flow may not be the end of the story. It could spark an entirely new set of questions and prompt innovative theories, pushing the boundaries of science even further. As we begin to grasp the complexity of dark flow, it could lead to a profound re-evaluation of our place in the universe, perhaps forcing us to reconsider not only the structure of the cosmos, but our own role within it. As we ponder the cosmic scale, we are reminded of the conditions required for life to exist beyond Earth. Life, as we understand it, depends on a delicate balance of elements, energy, and stable environmental conditions. These conditions form the foundation upon which life could potentially emerge on other planets or moons, far beyond the reach of our home planet. Water, in particular, is central to the existence of life. It acts as a solvent, enabling the chemical reactions that are necessary for biological processes. Without water, the complex molecules needed for life simply cannot form. This is why scientists place such emphasis on finding planets or moons where liquid water might exist, as it provides the most fundamental prerequisite for life as we know it. Moons like Europa, one of Jupiter's satellites, and the Martian surface have sparked particular interest due to the evidence of water beneath their icy crusts. But water alone is not enough. For life to thrive, it requires an energy source. On Earth, this energy is primarily derived from sunlight, which drives photosynthesis in plants. However, in the search for life beyond Earth, scientists are considering other forms of energy that could support life, such as the heat produced by geological activity deep within planets, or even chemical energy sourced from minerals. These alternative energy pathways could allow life to flourish in environments that would otherwise seem inhospitable. In addition to water and energy, the right chemical elements must be present. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are essential for building the molecules that make up living organisms, including proteins and nucleic acids. Without these elements, complex life simply cannot exist. As scientists scan the atmospheres of distant planets, they look for signs of these key elements, searching for organic molecules that might suggest the presence of biological processes. This search for chemical signatures is a critical aspect of the hunt for life beyond Earth. Stable environmental conditions are another essential factor. Life requires a climate that is not only suitable for biological processes, but also shielded from harmful radiation. This is why planets located in the habitable zone of their stars, often referred to as the Goldilocks zone, are of particular interest. In this region, conditions are just right, neither too hot nor too cold for liquid water to exist, providing the perfect environment for life to thrive. Time is another critical component in the equation. For complex life forms to evolve, there must be sufficient time for evolution to take place. This requires a stable orbit and climate over millions or even billions of years, allowing the slow process of natural selection to unfold and lead to the development of complex organisms. Without this long time scale, life would never have had the opportunity to evolve to the level of complexity seen on Earth. Thus, the search for life beyond Earth is a search for these specific conditions. It's a quest to find places where liquid water, A reliable energy source, essential chemical elements, stable environmental conditions, and enough time have come together in the right proportions to allow life to emerge. Scientists continue to explore the cosmos, hoping to identify planets and moons where these conditions might align, offering the possibility of extraterrestrial life. The search for life beyond Earth has become one of the most exciting and challenging endeavors in modern science. Over the years, astronomers have made significant strides in identifying potential candidates for life. The discovery of thousands of exoplanets, planets that orbit stars outside our solar system, has opened up new possibilities for habitable worlds. Some of these exoplanets share characteristics that resemble those of Earth, such as size, temperature, and composition, suggesting they may have environments that could support life. In addition to looking at exoplanets, the exploration of our own solar system has yielded important insights into the potential for life beyond Earth. For instance, the discovery of extremophiles, organisms that thrive in extreme conditions on Earth, has challenged long-held assumptions about where life can exist. These organisms survive in environments previously thought to be too harsh, such as deep-sea vents, boiling hot springs, and icy tundras. If life can exist in these extreme conditions on Earth, it stands to reason that similar forms of life might thrive in places like the icy plumes of Europa or in the subterranean oceans of distant moons. Despite these promising discoveries, definitive evidence of extraterrestrial life remains elusive. Yet each new mission, whether it's a rover on Mars, a probe studying the atmospheres of exoplanets, or a spacecraft exploring the icy moons of the outer solar system, brings us one step closer to answering this age-old question. Each mission not only improves our understanding of where life could exist, but also deepens our knowledge of the conditions required for life to survive and thrive. The quest for life beyond Earth is not just about finding extraterrestrial organisms. It is about understanding the broader potential for life in the universe and our own place within it. As scientists continue to explore the cosmos, they employ a variety of innovative strategies and technologies, such as studying planetary atmospheres, analyzing soil and rock samples for chemical traces of life, and using powerful telescopes to monitor exoplanetary systems. The more we learn about the universe, the more we realize that life, in all its forms, could exist in places we never imagined. The discovery of extraterrestrial life, when it comes, will not only be a scientific breakthrough, it will be a paradigm-shifting moment that changes our understanding of life, the universe, and everything in between. Moreover, researchers are intensely focused on studying the atmospheres of exoplanets, particularly to identify specific gases linked to biological processes. Among these gases, oxygen and methane are of particular interest, as their simultaneous presence in large quantities could potentially indicate the existence of life. These two gases are highly reactive, and their tendency to interact with one another makes it unlikely that they would coexist in abundance unless continuously replenished by living organisms. This gives scientists an exciting avenue to explore. The detection of such gases could be a sign that life, or at least the conditions necessary for life, exists on distant worlds. Another fascinating approach involves the search for signals from advanced extraterrestrial civilizations. Using powerful radio telescopes, scientists are actively scanning the cosmos for patterns in the radio waves they receive, hoping to detect deliberate communication. The discovery of such signals would offer compelling proof that intelligent life exists beyond Earth, validating the long-held assumption that we may not be alone in the universe. Astrobiology, a discipline dedicated to exploring the potential for life in the universe, combines knowledge from a range of fields: biology, chemistry, and planetary science. By drawing on these diverse areas of study, astrobiologists develop models that predict where and how life might emerge in environments vastly different from Earth. These models help refine our search for life beyond our planet, shedding light on the kinds of conditions that might foster life and the forms it might take in far-flung corners of the galaxy. Through these varied methods, scientists are constantly expanding their understanding of life beyond Earth, working tirelessly to unlock the secrets of the universe. Their search isn't just about finding life. It's about unraveling the larger mystery of our existence and understanding our place in the cosmos. It's a search that transcends science, touching on philosophical and existential questions that have fascinated humanity for millennia. The Fermi paradox stands as one of the most compelling puzzles in the study of extraterrestrial life. Named after the physicist Enrico Fermi, it highlights the stark contrast between the high probability that extraterrestrial civilizations should exist and the complete absence of evidence for their presence. Given the sheer number of stars and planets in our galaxy alone, one would logically expect intelligent life to be common. So, the question arises, where is everyone? Various theories have been proposed to address this paradox. One possibility is that intelligent life is incredibly rare. Perhaps the conditions required for life, and especially for intelligent life, are so unique that we are witnessing an extraordinary, perhaps one-off event in the history of the cosmos. While simple life forms might be common throughout the universe, they may never evolve into the complex, technologically advanced civilizations that we imagine. This would mean that we as humans are exceptionally fortunate to be witnessing such an event. Alternatively, it could be that civilizations with advanced technology capable of interstellar communication or travel don't last long enough to make contact. Civilizations may rise and fall, extinguishing themselves before they have the opportunity to reach out to the stars. In this scenario, we could be living in a fleeting window of time where human civilization is capable of space exploration and communication. But that window is so narrow that it's unlikely we will ever cross paths with other civilizations. Another possibility is that intelligent life does exist, but for some reason, extraterrestrial civilizations choose not to contact us. This could be a deliberate decision, perhaps driven by a kind of cosmic prime directive, akin to the rule against interfering with developing civilizations that appears in many works of science fiction. It's also conceivable that extraterrestrial civilizations may be using forms of communication that are beyond our current technological capabilities, rendering their signals undetectable by our instruments. Yet another intriguing theory involves the idea of the Great Filter. This concept suggests that there is a critical evolutionary step that most forms of life fail to overcome. This filter could lie behind us, indicating that the leap from simple life forms to intelligent civilizations is exceedingly rare. Alternatively, the filter could be ahead of us, suggesting that most civilizations inevitably self-destruct before they can achieve the technological capacity for interstellar travel. If this is the case, the prospects for humanity's future may be dim, as we could be on the verge of self-destruction. There's also the possibility that intelligent civilizations deliberately avoid detection. Perhaps they are quietly exploring the universe or living in highly advanced, hidden societies, intentionally steering clear of contact with less developed species like us. The truth behind the Fermi paradox remains elusive, but it continues to provoke scientists and thinkers alike to delve into the mysteries of life beyond Earth. The discovery of extraterrestrial life, should it ever occur, would have profound and far-reaching implications for human society. Initially, such a discovery would likely spark a wave of excitement, curiosity, and perhaps fear. This groundbreaking revelation would challenge our deepest assumptions about what it means to be human. For centuries, we have viewed ourselves as the pinnacle of life in the universe, and the realization that we are not alone would force us to reevaluate our place in the cosmos. On a social level, the discovery could unite humanity in ways previously unimaginable. The knowledge that we share the universe with other intelligent beings might foster a sense of global community, with people from all backgrounds coming together to explore this newfound reality. National borders, once a source of division, could begin to seem irrelevant in the face of a shared identity as inhabitants of Earth. Humanity's sense of isolation could evaporate as we join forces in the pursuit of knowledge about the wider universe. Culturally, this revelation would likely lead to a surge in artistic, philosophical, and literary expression. New narratives would emerge, exploring the implications of our newfound understanding of the cosmos. How would we coexist with other intelligent species? What would be the impact on our concept of identity, both as individuals and as a species? The discovery could give birth to entire new genres of art and literature as we struggle to express and comprehend this earth-shattering realization. Religiously, the discovery of extraterrestrial life could spark new debates and interpretations. The existence of other life forms would challenge long-standing beliefs about the uniqueness of humanity and our place in the grand scheme of creation. It could lead to new theological discussions about the nature of existence, creation, and the meaning of life itself. Technologically, the implications could be even more profound. If contact with extraterrestrial beings were possible, it could lead to unprecedented advances in science, medicine, and technology. The knowledge shared by extraterrestrial civilizations could inspire innovations we cannot yet imagine, propelling humanity into a new era of discovery. This prospect could fuel the aspirations of future generations, motivating them to continue exploring the stars, eager to learn from other civilizations' advancements. However, such a monumental discovery would also come with its own set of challenges. The realization that extraterrestrial life exists could induce fear, mistrust, and even conflict. How would we protect ourselves from potential threats? Could the interactions with these advanced civilizations change the very fabric of society? Ethical considerations would also arise. How should we approach these beings, and how might we share our planet and its resources with them? The discovery of extraterrestrial life would undoubtedly act as a catalyst for change, influencing everything from social structures to cultural identities to scientific pursuits. It would pose complex emotional and ethical dilemmas, forcing us to reconsider how we live and interact with each other, both on Earth and in the greater universe. As we ponder these possibilities, we are reminded that the discovery of life beyond Earth would mark the beginning of an entirely new chapter in human history. It would invite us to rethink everything we know about life, existence, and our role in the universe. Gravity, one of the fundamental forces of nature, plays a crucial role in shaping the universe. It is the invisible force that binds the cosmos together, influencing the movement of objects, the formation of celestial structures, and even the life cycles of stars and galaxies. To understand gravity's profound impact, imagine a vast cosmic tapestry woven with countless threads. Every piece of matter, from the smallest particle to the largest galaxy, exerts a pull on these threads, creating a structure that governs the universe. The most apparent effect of gravity is in the formation of celestial bodies. Planets, stars, and galaxies are born from vast clouds of gas and dust that, over time, begin to clump together due to gravity. As more and more material is drawn in, the gravitational pull strengthens, attracting even more matter. This process is like a snowball rolling downhill, gathering more snow as it moves until large, complex structures emerge. Once these structures are formed, gravity continues to shape their behavior. It keeps planets in orbit around their stars, stars within their galaxies, and galaxies within larger cosmic structures. Without gravity, all these celestial bodies would drift apart, dissolving into the void of space, throwing the entire universe into disarray. Gravity also has a more subtle but equally profound effect on the fabric of space and time itself. When we encounter extremely dense objects like black holes or neutron stars, the warping of space becomes so intense that it alters our perception of distance and time. Time, for example, appears to slow down as you approach a black hole, and the very fabric of space itself stretches and warps, defying the normal rules of physics. This remarkable phenomenon shows just how deeply gravity influences not only the physical universe, but also our understanding of reality itself. Gravity, a fundamental force that holds the universe together, plays a pivotal role in shaping the very structure of the cosmos. Its influence stretches far beyond the scale of planets, stars, and galaxies. It extends across the vastness of the universe, orchestrating a grand cosmic dance. At the most fundamental level, gravity determines the organization of the cosmic web, a complex network of galaxy clusters and vast filaments that are woven together through the force of gravity. This web connects distant corners of the universe, and gravity is the invisible thread that binds these distant islands of matter. It governs how these immense groups of galaxies come together, collide, and eventually coalesce into superclusters, shaping the universe's large-scale structure. As the universe continues to expand, gravity remains an unyielding force, working against this expansion by relentlessly pulling matter together. While the universe is stretched outward by the force of dark energy, gravity acts like an opposing force, attempting to rein in the runaway expansion. In this sense, gravity is not merely a force, it is a cosmic sculptor, molding the very fabric of reality. From the swirling, majestic spirals of galaxies to the intricate mechanics of our very own solar system, gravity is the unseen architect of the cosmos, shaping the motions and interactions of celestial bodies. Understanding gravity offers a window into the delicate balance that governs all movement in the universe. It allows us to appreciate how celestial objects interact with one another, how stars are born and die, and how entire galaxies are held together in a delicate cosmic dance. Yet, despite its importance, gravity remains shrouded in mystery. It is one of the fundamental forces in nature, yet its full nature and the ways it fits into the broader framework of physics remain elusive. One of the most significant challenges is reconciling gravity with quantum mechanics, the theory that governs the behavior of the smallest particles in existence. While we have a solid understanding of gravity's effects on large-scale objects like planets, stars, and galaxies, its relationship with the quantum world is less clear. Gravity operates on an entirely different scale, and we currently lack a unified theory that bridges the enormous, sweeping forces of gravity with the subatomic, probabilistic nature of quantum particles. This search for a theory of quantum gravity has become one of the foremost quests in modern physics. Another profound mystery involves the nature of dark matter. Observations suggest that the universe contains far more mass than we can observe directly, and this unseen mass seems to play a crucial role in shaping the gravitational behavior of galaxies. Dark matter doesn't emit light, nor does it interact with electromagnetic forces in any detectable way, making it invisible to traditional means of observation. Despite its elusiveness, dark matter's gravitational influence is undeniable, and it is believed to account for the majority of the mass in the universe. The question remains, what is dark matter? Could it be made up of entirely new particles that have yet to be discovered, or is our understanding of gravity itself flawed at cosmic scales? Further complicating our understanding of the universe is the presence of dark energy, a mysterious force that appears to be driving the accelerated expansion of the cosmos. While the universe continues to stretch outward at an ever-increasing rate, the nature of dark energy remains one of the greatest unsolved puzzles in cosmology. Is dark energy a new form of energy that we don't yet understand? Or could it signal that our grasp on gravity needs to be adjusted on the largest cosmic scales? At the extreme ends of the universe, gravity's behavior becomes even more perplexing. Near objects like black holes, where gravity is so intense that not even light can escape, our current theories of physics break down. The intense warping of space and time near these objects suggests that there are fundamental rules governing gravity that we have yet to fully comprehend. These enigmatic regions challenge our understanding of space-time, hinting that there may be unknown principles at play that govern the universe's most extreme environments. These unresolved questions do more than highlight the limits of our current knowledge. They open up vast possibilities for future discoveries. The pursuit of a deeper understanding of gravity could one day lead to groundbreaking revelations about the universe itself. As we continue to probe this fundamental force, we may uncover new truths that completely reshape our view of reality. Gravity and relativity are intertwined in a way that fundamentally alters our understanding of space and time. At its core, gravity is the force that pulls objects toward each other, a force that operates on everything with mass, from the tiniest particles to the most massive stars. But Einstein's theory of general relativity deepens our understanding, describing gravity not as a conventional force, but as a warping of space and time. Imagine a heavy ball placed on a trampoline. The ball creates a depression, and smaller objects nearby are drawn toward it. In this analogy, the trampoline represents space-time, and the ball is a massive object like a planet or a star. Massive objects warp the fabric of space-time around them, causing nearby objects to follow curved paths. This curvature of space-time affects not only the immediate vicinity of large bodies, but also has a profound influence on the dynamics of entire galaxies and galaxy clusters. On a cosmic scale, this means that the presence of massive objects like galaxies bends the very fabric of the universe itself. For example, when light from a distant star passes near a massive galaxy, the warping of space-time caused by the galaxy can cause the light to bend. This phenomenon, known as gravitational lensing, allows astronomers to study galaxies that would otherwise be hidden from view, offering a unique window into the far reaches of the universe. Additionally, as objects with mass move through this curved space-time, they experience time differently, a phenomenon known as time dilation. In regions with stronger gravitational fields, time passes more slowly compared to areas with weaker gravitational forces. This means that a person near a massive object would age more slowly than someone farther away, providing yet another layer of understanding about how the universe operates at the most fundamental level. The relationship between gravity and relativity is crucial for understanding some of the most enigmatic phenomena in the universe, such as black holes. These regions of space exhibit such extreme gravitational forces that not even light can escape their grasp. Understanding how gravity interacts with relativity in these environments is key to unlocking the mysteries of these fascinating objects. In this way, the study of gravity and relativity offers a powerful lens through which to explore the workings of the cosmos, revealing how even the largest galaxies and the smallest particles are linked through the universal fabric of space-time. One of the most exciting discoveries in recent years has been the detection of gravitational waves. These ripples in space-time were first predicted by Einstein more than a century ago, and they occur when massive objects accelerate, such as when two black holes collide or when neutron stars orbit one another. Imagine the ripples created by throwing a stone into a calm pond. Similarly, gravitational waves spread outward from the point of impact, distorting the fabric of space-time as they travel across the universe. These waves move at the speed of light, carrying information about the events that created them. The direct detection of gravitational waves represents a monumental achievement in the field of physics, opening up new possibilities for understanding the universe. Unlike traditional astronomy, which relies on light to gather information, gravitational waves offer a completely different perspective on the cosmos. They allow us to study events that are otherwise invisible, such as the mergers of black holes or the collisions of neutron stars. This new form of observation has already provided groundbreaking insights into the rate of expansion of the universe and the nature of stellar evolution. Gravitational waves have fundamentally altered our approach to studying the universe. By providing clues about the most violent and dynamic processes in space, they offer a deeper understanding of the very foundations of space and time itself. This new observational method enriches our cosmic narrative, shedding light on phenomena that were once hidden from our view and expanding our knowledge of the universe. If we can eventually unravel the mysteries of gravity, the potential advancements in science could be revolutionary. Our understanding of gravity shapes everything we know about the universe, from the fall of an apple to the orbits of distant stars. But there is still so much left to learn. For example, understanding how gravity interacts with other fundamental forces, such as electromagnetism, could lead to groundbreaking discoveries. One potential advancement might come in the form of new technologies, particularly in transportation. If we could learn to manipulate gravity, it might pave the way for new spacecraft that can travel vast distances at speeds previously thought impossible. This could allow humanity to explore distant planets or even venture to other star systems in a fraction of the time it currently takes. As we continue to explore gravity's mysteries, we may one day find ourselves on the brink of a new era in space exploration and understanding of the universe itself. The journey to uncover the secrets of gravity is far from over, but with each discovery, we come closer to revealing the fundamental forces that shape the very fabric of reality. Gravity, a force so fundamental yet so mysterious, holds the keys to understanding many aspects of the universe. Its pervasive influence touches every corner of space, yet it remains largely misunderstood. The potential of gravity, if fully unlocked, could open doors to revolutionary advancements in energy production. Gravity's strength could serve as an unexpected but powerful source for harnessing energy, inspiring new methods for sustainable and efficient energy generation. These innovations could change not only how we power our world, but also the very way we think about the future of technology and resources. As we delve deeper into the nature of gravity, we uncover more than just the mechanics of objects falling or planets orbiting. A profound understanding of gravity could reveal the intricacies of space-time, the fabric that weaves together the three dimensions of space and the dimension of time itself. This insight could shed light on some of the universe's greatest mysteries: black holes, dark matter, and dark energy, phenomena that remain beyond our full comprehension. These elusive aspects of the cosmos continue to puzzle scientists, but a deeper grasp of gravity might unlock the answers hidden within them, offering new theories and models that could change the way we view reality. Furthermore, the implications of understanding gravity extend beyond the abstract into the origins of the universe itself. Knowledge of gravitational forces could provide clues to the conditions that existed just moments after the Big Bang, offering new perspectives on the birth of the cosmos. The quest to understand gravity could reveal the fundamental nature of the universe's creation, advancing our understanding of existence itself. It is a journey that could push the boundaries of physics, cosmology, and even our very conception of what is possible. As we explore the intricate relationship between gravity and the fabric of space-time, we might also unlock groundbreaking discoveries in technology and energy systems. Every new insight into how gravity works could transform the way we interact with the universe on a technological level, fostering innovations that touch everything from energy generation to the very tools we use to explore space. The opportunities that lie within this field are as boundless as the universe itself, with potential far beyond our current imaginations. When we think about light and its journey across the cosmos, we are reminded of the delicate balance of forces that govern the universe. Light, in its essence, is a form of energy that travels in waves, moving across vast stretches of space at incredible speeds. The light we observe today began its journey millions, even billions of years ago. These streams of photons, which we now recognize as light, race through the emptiness of space, defying the vast distance between celestial bodies. Unlike sound, which relies on a medium like air to travel, light moves effortlessly through the vacuum of space, allowing it to cross immense voids between stars, galaxies, and other cosmic structures. However, the path of light is not always a straight one. As light travels through the universe, it is often altered by the immense gravitational forces of massive objects like stars, galaxies, or black holes. These objects can bend the path of light, a phenomenon known as gravitational lensing. The gravity of these colossal bodies distorts the light that passes near them, sometimes splitting it into multiple images or distorting its shape. This bending effect not only reveals the presence of these massive objects, but also gives us valuable information about the nature of the universe's structure. Gravitational lensing serves as a cosmic magnifying glass, allowing us to observe distant galaxies and stars in ways that would otherwise be impossible. Light also interacts with the gas and dust scattered throughout space, particularly in regions where stars are being born. These regions, known as nebulae, are often shrouded in a thick haze of interstellar dust that scatters or absorbs light, altering its color. The resulting light can shift in wavelength, producing vivid shades of red, blue, and green, which we observe as the glow of nebulae. This colorful display is not just a beautiful visual phenomenon, it holds critical information about the processes taking place within these cosmic nurseries. By analyzing the way light behaves in these regions, scientists can learn about the temperature, composition, and evolution of stars and other celestial bodies. The journey of light is a journey through time. The light that reaches our eyes today has traveled across vast distances, and in doing so, it carries with it a record of the universe's history. Each flicker we see in the night sky is a glimpse into the past, a moment frozen in time. The farther we look into space, the further back in time we are peering, observing stars and galaxies as they were millions or even billions of years ago. Light from distant stars is not merely a source of illumination. It is a time capsule, preserving the history of the cosmos as it hurtles through space. When we observe light, we are not just seeing the objects that emit it, but we are also gaining crucial insights into their nature. The light we observe reveals the composition, temperature, speed, and even the motion of distant celestial bodies. By studying the spectrum of light, scientists can determine what elements make up a star or galaxy. Each element emits or absorbs light at specific wavelengths, much like a unique fingerprint, and by analyzing these patterns, astronomers can identify the building blocks of the universe. In addition to revealing composition, the color of light also provides valuable clues about temperature. Hotter objects emit light at shorter wavelengths, which we perceive as blue or violet, while cooler objects emit light at longer wavelengths, which appear red. This principle is crucial for determining the temperature of distant stars and other celestial bodies, providing us with a window into the conditions that exist on faraway worlds. Similarly, the motion of celestial objects can be gauged by the way their light shifts. When an object moves away from us, its light is stretched, causing a red shift, while objects moving toward us exhibit a blue shift. By measuring these shifts, scientists can determine not only the speed and direction of an object's movement, but also its distance from us. The concept of redshift and blueshift is a fundamental tool in our understanding of the expanding universe. The Doppler effect, which explains the shift in the wavelength of light due to the relative motion of an observer and a light source, plays a crucial role in cosmology. As galaxies move away from us, their light becomes redshifted, a clear sign that the universe is expanding. This discovery, one of the cornerstones of modern cosmology, has reshaped our understanding of the universe's origin and its ongoing evolution. However, not all objects in the universe are receding. Some are moving toward us, and their light is blue shifted. This phenomenon is less common, but still valuable. By studying these shifts, astronomers can infer the motion of celestial bodies and gain insights into the structure and dynamics of the universe. The greater the redshift, the faster an object is moving away, providing critical information about the rate of cosmic expansion and the fate of the universe. In addition to redshift and blueshift, astronomers have developed methods to measure vast distances in space using light. One of the most powerful tools at their disposal is parallax, a technique that involves observing the apparent shift in the position of a nearby star relative to more distant stars as Earth orbits the Sun. By measuring this tiny shift, scientists can calculate the distance to the star with remarkable accuracy. Parallax, in essence, turns light into a ruler, allowing us to measure the vastness of space with precision. Light is not just a tool for observing the universe. It is a messenger from the distant past, a bridge between the present and the history of the cosmos. The study of light, from its interactions with gravity to its role in measuring distances and understanding the universe's expansion, is essential for unlocking the mysteries of the cosmos. Through light, we gain access to the deepest secrets of the universe, shaping our understanding of the past, present, and future of everything that exists. Astronomers employ a remarkable tool in their quest to understand the vast expanses of the universe: standard candles. These are specific types of stars, such as certain kinds of supernovae, whose inherent brightness is well known. By comparing their expected brightness to how brightly they appear from Earth, scientists can calculate their distance from us. If these stars appear dimmer, it's a clear indication that they are farther away, much like how streetlights in the distance seem less bright than those nearby. This comparison of apparent brightness to actual brightness provides an invaluable method for measuring the enormous distances that separate celestial objects. When it comes to the measurement of time in the cosmos, scientists frequently rely on the speed of light. This is particularly significant when observing distant astronomical phenomena, like supernovae. The light from these distant events has traveled for years, often millions or even billions of years, before reaching our eyes. The time it takes for light to traverse such vast distances offers a crucial insight into when the event actually occurred. For instance, if we observe light from a star that is millions of years old, we are seeing light that was emitted millions of years ago, offering us a window into the past. This concept of looking back in time, made possible by the light traveling through space, allows astronomers to construct a profound understanding of the universe. Through these observations, we not only learn about distant galaxies and stars, but also establish a connection with events happening far beyond our own world. Yet, studying light from the farthest reaches of the universe comes with significant challenges. First and foremost, the immense distances involved mean that the light we observe can take billions of years to reach us, effectively making us spectators of the distant past. This long journey introduces a series of complications when interpreting the light we receive. As the light travels, it may undergo changes, and by the time it reaches Earth, it may appear different from how it originally was when emitted. In addition, the space between us and these distant objects is filled with cosmic material such as gas and dust. These particles can absorb or scatter light, causing distant objects to appear dimmer or altering their colors. Astronomers must account for these distortions in order to accurately interpret the true nature of the light they observe. Another significant challenge stems from the ongoing expansion of the universe. As the universe stretches, the light emitted by distant objects is also stretched, a phenomenon known as redshift. This stretching of light causes it to shift toward the red end of the spectrum, and sometimes even beyond the range of visible light, making it impossible to detect with standard telescopes. To capture this shifted light, astronomers rely on specialized instruments that can detect these wavelengths. However, analyzing the data gathered from these instruments often requires complex calculations and advanced techniques. Furthermore, the limitations of our technological tools add another layer of complexity. Telescopes need to be powerful enough to collect the faint light from distant objects, but they must also contend with atmospheric distortion. The Earth's atmosphere can blur the images captured by telescopes, complicating the process of gathering clear data. To overcome this, scientists often place telescopes in space, where they are free from atmospheric interference, allowing for clearer and more accurate observations. These various factors combine to create a challenging puzzle for scientists. They must be adept at interpreting faint, distorted signals from the far reaches of space, while simultaneously leveraging advanced technology to uncover the mysteries of our universe's most remote corners. One of the most mind-boggling phenomena in the realm of quantum physics is quantum entanglement. Imagine two particles that are so deeply connected that their states are intrinsically linked, much like two dancers moving in perfect harmony. When one dancer changes position, the other dancer adjusts instantly, regardless of how far apart they are. This instantaneous connection between particles is what scientists refer to as entanglement. In classical physics, which governs our everyday experiences, objects are typically independent unless they interact with one another. For example, if you throw a ball, its trajectory depends on the forces acting on it at that moment, such as gravity or air resistance. However, in the quantum world, the state of one particle can influence the state of another, even if the particles are separated by vast distances. This phenomenon challenges our conventional understanding of space and time. One of the most striking aspects of quantum entanglement is its apparent defiance of the principle that information cannot travel faster than the speed of light. When particles are entangled, measuring the state of one particle causes an instantaneous change in the state of the other, regardless of the distance between them. This rapid transfer of information seems to contradict what we know about the speed of light and raises profound questions about the nature of reality itself. Entanglement suggests that at a fundamental level, the universe is far more interconnected than we once imagined. It forces us to reconsider our understanding of space, time, and the very fabric of the universe. The implications of entanglement extend far beyond the realm of physics and into the philosophical. It challenges us to rethink not just how particles interact, but how we perceive the universe as a whole. The implications of quantum entanglement stretch far beyond the laboratory and into the very structure of reality. Consider two entangled particles that behave as though they are connected in a way that defies our understanding of space and time. When one of these particles is measured, it provides information about the other particle instantaneously, regardless of how far apart they may be. This phenomenon leads us to question the fundamental nature of space itself. If two particles can be so deeply linked, could space, the medium through which information traditionally travels, not be as fundamental as we once thought? In other words, could space be an emergent property arising from deeper, more intricate relationships between fundamental particles? Furthermore, quantum entanglement compels us to reconsider our understanding of time. Since the connection between entangled particles appears instantaneous, it challenges our conventional ideas of cause and effect. If information can travel instantaneously, regardless of the time it would take to travel through normal space, it raises questions about the very nature of time itself. Could it be that time, like space, is not as absolute as we have always believed? Could our understanding of cause and effect be incomplete or flawed? These questions represent some of the most profound challenges in modern physics and philosophy. Scientists are still grappling with the full implications of quantum entanglement, exploring how this strange phenomenon might reveal hidden dimensions or unknown aspects of the cosmos. If particles can be connected in ways that defy the traditional limits of locality and separateness, could this suggest that space itself is a more complex, interconnected entity than we realize? Could it point to deeper, more intricate relationships between particles that form the very fabric of the universe? To investigate these ideas, scientists have devised several innovative experiments, particularly on a cosmological scale. One significant experiment involved the use of pairs of photons, particles of light. These photons were entangled, meaning that their properties were linked in a way that allowed them to influence each other instantaneously. One photon was sent to a distant location, while the other remained behind. By measuring the properties of the traveling photon and comparing them with the measurements taken from the stationary photon, researchers found that the results of the measurements on one photon seemed to influence the other, regardless of the distance between them. This remarkable experiment demonstrated that entanglement can occur even over vast distances. Another fascinating approach involved studying pairs of photons that originated from distant cosmic events, such as the radiation emitted by galaxies billions of light years away. By using powerful telescopes, scientists observed the light coming from these distant sources, looking for patterns that would indicate quantum entanglement. These experiments offer critical insights into whether entangled particles behave as predicted by theory, even when separated by vast stretches of space. By analyzing the results, researchers hope to unravel more about the true nature of entanglement and what it can reveal about the underlying structure of the cosmos. Experiments have expanded in scope, venturing into the very foundations of quantum theory. The focus has shifted to scrutinizing the behavior of entangled particles under a variety of conditions. These investigations are not just about testing the principles of quantum mechanics. They aim to uncover whether local hidden variables could potentially explain the peculiar correlations between entangled particles, or if the results further validate the bold predictions of quantum mechanics, particularly when applied across vast cosmic scales. By conducting these experiments, researchers are stepping into uncharted territory, offering profound insights into the fundamental nature of reality itself. The ability to successfully observe quantum entanglement under such extraordinary circumstances carries vast implications. It has the potential to fundamentally reshape our understanding of the universe at both the smallest and largest of scales. When particles interact in this deeply intertwined way, what seems like an instantaneous exchange of information, no matter the distance between them, raises intriguing questions. Could this phenomenon allow for communication across cosmic distances, across billions of light years, in a manner that defies our conventional understanding of space and time? The quest for knowledge in this realm is far from complete, but it is accelerating. With each new discovery, we are drawn deeper into the mysteries of the universe that lie at the crossroads of quantum mechanics and the vast expanse of the cosmos. Quantum entanglement, a phenomenon where two particles become so deeply interconnected that the state of one instantly influences the state of the other, remains one of the most enigmatic aspects of modern physics. Regardless of the distance between them, be it millimeters or light years, this instantaneous influence challenges our most basic assumptions about the fabric of reality. To grasp the nature of this connection, imagine two dancers performing an intricate routine. No matter how far apart they are, their movements are perfectly synchronized, as if guided by an unseen force. This strange behavior forces us to reconsider everything we think we know about space, time, and the universe itself. As researchers continue to explore this perplexing phenomenon, they are not merely testing the boundaries of quantum physics, they are uncovering deeper truths about the interconnectedness of the universe. The prevailing theories now suggest that the universe may not be composed of isolated, independent particles, but rather is an intricate web of connections, a vast tapestry where every thread is woven together in ways we are only beginning to fathom. This idea transcends the confines of traditional physics, which has long treated particles as individual self-contained units. Entanglement also forces us to reconsider our understanding of information and reality. In the world of entangled particles, information about one particle's state is instantaneously shared with its partner, regardless of the distance between them. This seems to defy the speed of light limitation, raising fundamental questions about the very nature of causality itself. Could events in the universe unfold in ways that are not solely determined by local interactions, as traditional physics suggests? These questions are not theoretical. They are at the heart of ongoing experiments that could unlock entirely new realms of understanding. For example, as scientists explore the implications of quantum entanglement, some are considering its potential role in understanding not just the microcosm of atomic particles, but also larger cosmic phenomena. The very structure of space-time itself might be influenced by the entangled states of distant particles, offering clues about how galaxies, stars, and black holes evolve and interact. The possibility that entangled particles could offer insights into the elusive mysteries of dark matter and dark energy, two of the most enigmatic forces in the universe, could lead to breakthroughs in our understanding of these invisible components that govern so much of the cosmos. In fact, the study of quantum entanglement could also illuminate the mysteries of gravitational waves, those ripples in space-time caused by the most violent events in the universe, such as black hole mergers or supernova explosions. If entanglement can be harnessed to enhance the sensitivity of instruments that detect these waves, we might be able to gain unprecedented insights into the most energetic and chaotic processes in the universe. This opens the door to new approaches to understanding black holes, the Big Bang, and the very origins of space and time itself. The potential for a unified theory that integrates quantum mechanics with general relativity, two pillars of modern physics that have long been seen incompatible, could be within our grasp. By studying entangled particles in the context of gravitational fields, we might be on the verge of solving some of the most profound mysteries about the universe. The more we learn about quantum entanglement, the more we realize that the boundaries of physics are not as rigid as once thought. The implications for our understanding of cosmology are vast. Galaxies, too, are shaped by a complex interplay of forces, from the initial conditions of the universe's birth to the present day. The formation and evolution of galaxies is a tale that stretches back to the very inception of the cosmos, beginning with the Big Bang. In the wake of this event, the universe was filled with hot, dense gas, primarily composed of hydrogen and helium. As the universe expanded and began to cool, small fluctuations in density began to emerge. These fluctuations, although minuscule, acted as the seeds for future galaxies. Over time, gravity played a crucial role, pulling in more gas and dust, amplifying these initial regions of higher density, which eventually grew into full-fledged galaxies. The gas that collapsed under its own gravity began to spin, a process familiar to anyone who has observed a figure skater spinning faster as they draw their arms inward. This spinning motion caused the material to flatten into rotating disks, the characteristic shape of many galaxies. As galaxies formed, they continued to evolve by merging with smaller galaxies, which added more stars and gas to their systems. This process of galactic merging was not without consequence. It triggered new star formation, as the gas clouds were compressed by the gravitational forces at play. As stars form and age, they produce new elements through the process of nuclear fusion. When they reach the end of their lives and explode in supernova, These elements are scattered across space, enriching the interstellar medium, the gas and dust that exists between stars. This process allows for the birth of new stars with more complex chemical compositions. But galaxies do not evolve in isolation. The presence of dark matter, which remains invisible to our eyes but can be detected through its gravitational effects, plays a central role in their formation and growth. Dark matter forms a vast halo around galaxies, influencing their stability and guiding their interactions with neighboring galaxies. The evolution of a galaxy is a slow, ongoing process, shaped by countless factors. As galaxies age, they may change in shape and size. Some grow into spiral or elliptical forms, while others take on irregular shapes as a result of interactions with other galaxies. These interactions, gravitational encounters that can distort the shapes of galaxies, are a fundamental aspect of galactic evolution. The balance between the birth of new stars and the removal of gas through supernova explosions, or the influence of a supermassive at the galaxy's center, is a delicate one, driving the long-term development of galaxies. Galaxies also exchange material during these interactions. When two galaxies collide or pass too close to each other, they can transfer gas, stars, and other elements, leading to new star formation and enriching their content. These processes are fundamental in shaping the diverse and complex structures we observe in the universe today. Ultimately, the evolution of galaxies is driven by a dance between gravity, gas dynamics, star formation, the explosive deaths of stars, and the invisible yet powerful influence of dark matter. Through these intricate processes, galaxies continue to grow and evolve, reshaping the cosmic landscape. Each collision, each merger, adds new layers of complexity, transforming galaxies into the magnificent structures that we can observe today, each one a unique and evolving entity, shaped by the forces of the universe itself. Galaxies, the colossal structures of stars, gas, dust, and dark matter, undergo dramatic transformations over the course of their existence. When galaxies collide, they can trigger a remarkable burst of star formation, creating a stunning display of light as new stars ignite in the crowded and chaotic environment created by the merger. These new stars shine with incredible brightness, illuminating the surrounding space, offering a dazzling glimpse into the cosmic forces at play. Over billions of years, these cosmic interactions not only influence the evolution of individual galaxies, but also shape the entire population of galaxies in the universe. The intricate dance between these vast cosmic entities leads to the creation of galaxy clusters, influencing the distribution of matter across space. Understanding these dynamic processes is key for astronomers as they strive to decipher the complex history of galaxies and the universe itself. Each galactic interaction, whether a collision or a gradual merging, leaves its mark, telling a story of evolution written in the stars. This story is bound together by the invisible yet powerful force of gravity. Scientists have made extraordinary discoveries about the life cycle of galaxies, unveiling their constant, ever-changing nature. The journey of a galaxy begins as a massive cloud of gas and dust, suspended in space, waiting for gravity to pull these elements together. As gravity acts on the materials, it ignites the formation of stars, marking the first chapter in a galaxy's evolution. Stars begin to form in clusters, their bright light illuminating the darkness of space. As these stars live and die, they play a crucial role in shaping the structure of the galaxy. Massive stars, in particular, have short lifespans, burning brightly before exploding in spectacular supernovae. These explosive events scatter heavy elements across the galaxy, enriching the interstellar medium and providing the essential ingredients for the next generation of stars and planets. This cosmic recycling process ensures that galaxies evolve and grow more complex over time. Interestingly, galaxies are rarely isolated in space. They often interact with and even merge with one another. These galactic collisions can spark a burst of star formation as the intense gravitational forces compress gas and dust, creating new stars in the process. Over time, these mergers can result in the formation of even larger galaxies, demonstrating how galaxies evolve and change through interactions within the cosmic neighborhood. However, as galaxies age, they may enter a quieter phase where star formation slows and older stars dominate the landscape. In such galaxies, the rate of new star formation diminishes, leading to the creation of elliptical galaxies. These galaxies, no longer producing stars at the same rapid rate, often take on a smooth, featureless appearance, lacking the spiral arms and vibrant activity found in their younger counterparts. Ultimately, the life cycle of a galaxy is an intricate and interconnected narrative, driven by a combination of gravity, stellar evolution, and cosmic collisions. Each phase of a galaxy's life lays the groundwork for the next, creating a continuous story that spans billions of years and offers a glimpse into the dynamic and ever-changing nature of the universe. As scientists continue to study the transformation of galaxies, they unlock more clues about the history of the cosmos, piecing together the events that have shaped the galaxies we see today. Galaxies themselves act like cosmic time capsules, containing within them the clues to their past. These clues reveal the processes that led to their current structure and offer insight into the broader evolution of the universe. To better understand the evolution of galaxies, let's look at the factors that influence their life cycles, including interactions with other galaxies, the birth and death of stars, and the movement of gas and dust within and between galaxies. When galaxies collide, the resulting merger can create new, more massive structures. This process not only reshapes the galaxies involved, but also helps scientists understand how galaxies grow and evolve over vast stretches of time. By observing these galactic mergers and studying their outcomes, astronomers can construct a timeline of galactic evolution. For instance, when we look at a young galaxy from the early universe, we may see a chaotic, irregular structure. Over time, as this galaxy interacts with others, it may begin to take on a more orderly appearance, perhaps transforming into the familiar spiral or elliptical shape that is common in the galaxies we observe today. In addition to these structural changes, the light emitted by a galaxy also provides valuable insight into its composition. This light allows astronomers to determine the types and ages of the stars within the galaxy, helping them track when stars first formed and how long they have been evolving. By analyzing the materials found within galaxies, such as heavy elements created by stellar processes, scientists can learn how many generations of stars have lived and died within each galaxy. These elements are the building blocks for new stars and planets, continuing the cycle of creation and destruction that characterizes the galaxy's life. Studying galaxies at different distances from Earth also enables scientists to peer into the past, as the light from distant galaxies takes billions of years to reach us. This means that when we observe these galaxies, we are not only seeing them as they are today, but as they were in the distant past. These distant galaxies provide a window into a time when the universe was still young, offering clues about its early conditions. This cosmic time travel allows scientists to understand the processes that shaped the universe in its infancy. For example, distant galaxies are often smaller and less developed than those closer to us, indicating that they were still in the early stages of star formation. Observing these galaxies helps astronomers piece together a picture of the universe shortly after its birth, when it was a hot, dense mix of particles. This early universe was a breeding ground for the formation of the first stars and galaxies, and studying it provides invaluable insights into the origins of the cosmos. As we continue to study galaxies and their evolution, we uncover the history of the universe itself. Galaxies are not just isolated objects. They are part of a larger cosmic narrative, one that tells the story of the universe's birth, growth, and transformation. Through the lens of galactic evolution, we can understand not only the life cycles of individual galaxies, but also the broader forces that have shaped the cosmos over billions of years. By examining the interplay between galaxies, stars, gas, and dust, scientists are building a more complete understanding of the universe's past, present, and future. Studying the light emitted by distant galaxies offers an extraordinary window into the heart of the universe. Through the detailed analysis of this light, scientists can decipher the chemical makeup of these far-off realms. Crucial elements such as hydrogen and helium, which were the fundamental building blocks of the early universe, are often present in vast quantities. These elements are the remnants of the cosmos's earliest moments, providing us with a snapshot of the materials that formed the stars and galaxies in the universe's infancy. As stars form and evolve, they undergo a remarkable process known as nuclear fusion. During this process, lighter elements like hydrogen and helium are fused together to form heavier elements, including carbon, oxygen, and iron. The presence and abundance of these heavier elements in distant galaxies offers scientists a unique insight into the evolution of stars and stellar processes over billions of years. These elements act as cosmic markers, helping us trace the birth, life, and death of stars, revealing how these processes have contributed to the development of a universe filled with a rich diversity of structures, stars, and galaxies. In many ways, distant galaxies are invaluable, not only for understanding the present structure of the universe, but also for unlocking the story of our cosmic origins. They provide a glimpse into an era when stars were just beginning to shine, illuminating a path that would lead to the complex and intricate tapestry of galaxies we observe today. Through their study, we can unravel the fundamental forces that shaped the universe, allowing us to better understand our own place in the grand cosmic scheme. The discovery of the universe's expansion is one of the most profound scientific breakthroughs of the 20th century. This revolution in our understanding of the cosmos began with the meticulous observations of astronomer Edwin Hubble. Using the most powerful telescopes of his time, Hubble studied the light coming from distant galaxies, and what he found changed everything. The light from these galaxies exhibited a distinct shift toward the red end of the spectrum, a phenomenon known as redshift. This redshift indicated that the galaxies were not stationary, but were moving away from us. Hubble's observations led to a groundbreaking realization. The farther a galaxy is from us, the faster it appears to be receding. This observation was the key to unlocking the mystery of an expanding universe. Hubble's findings suggested that, instead of remaining static, the universe was in a state of continual expansion, with galaxies drifting apart over time. His discovery not only reshaped our understanding of the cosmos, but also provided crucial evidence that aligned with the predictions made by Albert Einstein's theory of general relativity, which hinted at a dynamic and evolving universe. Together, Hubble's empirical evidence and Einstein's theoretical framework formed the foundation of a new understanding of the universe. The universe was no longer seen as a fixed, unchanging entity, but as a vast, ever-expanding expanse. This realization opened the door to new theories, including the Big Bang theory, and raised countless new questions about the nature of space, time, and the origins of the cosmos itself. The expansion of the universe is supported by several key pieces of evidence, each one adding to our growing understanding of the cosmos's changing nature. One of the most pivotal discoveries came from observing distant galaxies. Astronomers found that as galaxies moved farther away from us, they receded at faster speeds. This phenomenon, known as redshift, is a direct consequence of the expansion of space itself. As light from distant galaxies stretches into longer wavelengths, it provides a powerful indicator of the ongoing expansion of the universe. Another significant piece of evidence is the cosmic microwave background radiation, CMB, a faint glow that permeates the entire universe. This radiation is a remnant of the heat left over from the Big Bang, a faint echo of the universe's fiery birth. When scientists studied the CMB in detail, they uncovered patterns that confirmed a very hot and dense beginning for the universe, which has since expanded and cooled, leading to the universe we observe today. The discovery of the CMB served as an essential piece of the puzzle, confirming the universe's expansion from an incredibly hot and dense state. In addition to the CMB, the abundance of light elements such as hydrogen and helium also provides crucial evidence for the Big Bang theory. By calculating how much of these elements should have existed in the aftermath of the Big Bang, scientists were able to make predictions about their relative abundances today. Remarkably, the amounts of hydrogen and helium observed in the universe matched these predictions with great precision, further validating the Big Bang model. Finally, the structures we observe today, from galaxies to vast clusters of galaxies, also offer insight into the universe's expansion. The distribution and movement of these large-scale structures reveal the influence of cosmic expansion over billions of years. When scientists study the way galaxies and clusters of galaxies are arranged and how they move, they can trace back the history of the universe's growth and evolution, piecing together how expansion has shaped the universe's current structure. Taken together, These diverse lines of evidence form a coherent picture. The universe is not static, but constantly expanding. This realization has profound implications for our understanding of the cosmos and our place within it. As space itself expands, the very fabric of the universe stretches, pushing galaxies farther apart over time. The rate at which this expansion occurs is a fundamental factor in determining the age and future of the universe. The expansion rate of the universe, often referred to as the Hubble constant, plays a crucial role in cosmology. The Hubble constant measures the speed at which galaxies are receding from us, and it provides a key to understanding how quickly the universe is growing. A higher expansion rate could suggest that the universe is younger than we once thought, while a lower rate might indicate an older universe. This constant also affects our predictions about the universe's ultimate fate. As scientists continue to refine the value of the Hubble constant, it helps shape cosmological models that explain the universe's past, present, and future. If the universe continues to expand at an accelerating rate, it could lead to a scenario where galaxies drift apart forever, leaving a cold, desolate universe devoid of interactions and stars. On the other hand, if the expansion slows down, gravity might eventually take over, leading to a contraction of the universe in a process known as the Big Crunch, where galaxies would be pulled back together. Understanding the expansion rate is also crucial for exploring the role of dark energy, a mysterious force that is thought to be driving the acceleration of the universe's expansion. By studying how dark energy, dark matter, and radiation interact within the context of expansion, scientists are piecing together a more complete understanding of the cosmos and its underlying forces. The expansion rate, therefore, is not just a number, it is a central pillar of our understanding of the universe. It influences everything from the universe's age to its structure and, ultimately, its fate. As scientists continue to study the expansion of the universe, each new discovery refines our models, deepening our understanding of the vast and ever-evolving cosmos. As the universe expands, its implications become ever more profound. Imagine, if you will, a balloon being inflated. As the balloon expands, every point on its surface moves away from every other point, illustrating how galaxies are moving apart as space itself stretches. This continuous expansion means that, over enormous periods of time, galaxies that we currently observe may one day disappear from view. As the space between them continues to grow, the light they emit will take longer and longer to reach us until they eventually recede beyond our cosmic horizon, leaving only a handful of nearby galaxies visible. The implications of this endless expansion are staggering. Over the vast timescales of the universe, the night sky will change, and the distant galaxies we now see will fade from view. This gives rise to a poignant reflection. The universe, as we know it, is a fleeting moment in an eternal and ever-changing expanse. And yet, through the study of its expansion, we gain a deeper understanding of the fundamental forces at play, shaping not only the universe's past, but its future. As the universe continues to expand, it undergoes a cooling process that deeply influences the formation of new stars. This cooling, over time, affects the availability of raw materials needed to fuel the birth of new stellar bodies. As space stretches, these materials become increasingly sparse, spread thinner across the ever-expanding fabric of the cosmos. If the current trend of expansion persists unchecked, we may eventually reach a point where the birth of new stars becomes an incredibly rare occurrence. The energetic life cycles of existing stars will eventually come to an end, leading to a universe filled with nothing but burnt-out remnants, white dwarfs, neutron stars, and black holes. This stage of cosmic evolution brings us face to face with a chilling possibility, the heat death scenario. As galaxies drift further apart and stars burn out one by one, the universe will gradually approach a state of maximum entropy. In this state, energy will become evenly distributed across the cosmos, leaving no concentrated pockets to sustain the processes necessary for further change. With this loss of energy differentiation, the conditions that support life as we understand it will cease to exist. The universe will become a vast, cold, and empty space, devoid of stars, life, and the energetic processes that once powered it. This sobering future beckons as the ultimate fate of the cosmos, challenging our very understanding of existence. Equally intriguing is the role of dark energy in this expansion. Dark energy, the mysterious force responsible for accelerating the expansion of the universe, raises profound questions about the ultimate trajectory of the cosmos and our place within it. Despite being one of the most pervasive forces in the universe, dark energy remains largely elusive, evading a full understanding of its nature. However, it is clear that dark energy is crucial to our comprehension of the universe's future. Its presence is directly linked to the observed acceleration in the expansion of the universe. Galaxies are not simply moving apart at a steady rate. They are doing so at an increasing velocity, a phenomenon that challenges long-held assumptions about cosmic dynamics. The discovery of this accelerating expansion marks a major turning point in our understanding of the universe. For decades, scientists assumed that the expansion of the universe was a gradual and steady process. However, observations of distant supernovae, massive stellar explosions marking the end of a star's life, changed this narrative. These supernovae, acting as cosmic beacons, revealed that the universe's expansion is not slowing down as once expected, but rather accelerating. The supernovae appeared fainter than anticipated, implying that they were farther away than previously thought. This observation provided compelling evidence that the universe was expanding at an increasingly rapid rate. This accelerated expansion has been attributed to dark energy, which is believed to constitute a significant portion of the universe's total energy content. While the exact properties of dark energy remain mysterious, its influence is undeniable. Instead of gravitational forces pulling galaxies together, dark energy pushes them apart, causing an ever-widening rift in the fabric of the cosmos. This discovery has forced scientists to reconsider and refine their models of the universe, shifting the focus to understanding dark energy's role in shaping cosmic evolution. Moreover, the cosmic microwave background radiation offers a crucial piece of the puzzle. This faint glow, a remnant of the Big Bang, acts as a snapshot of the infant universe, providing invaluable insights into the distribution of matter and energy shortly after the universe's inception. By refining measurements of this radiation, scientists have been able to track the universe's expansion history, revealing not only that the universe expanded, but that it did so at an accelerating pace. These combined observations from supernovae to background radiation have cemented the idea that the universe is not a static entity, but a dynamic, ever-evolving system. Every new discovery pushes the boundaries of our understanding, reshaping our view of the cosmos and its intricate forces. Among the most fascinating objects in the universe are neutron stars, remarkable remnants of massive stars that have undergone catastrophic supernovae. Unlike stars like our Sun, neutron stars are not merely stellar remnants. They are compact giants, dense and mysterious, with properties that challenge our fundamental understanding of matter and physics. When a star with a mass significantly greater than our Sun reaches the end of its life, it can no longer sustain the balance between the outward pressure from nuclear fusion and the inward pull of gravity. The core collapses under its immense gravitational force, compressing until protons and electrons merge to form neutrons. This collapse results in the birth of a neutron star, an incredibly dense and compact object that can pack more mass than the Sun into a volume no larger than a small city. What makes neutron stars so intriguing is their extreme density. A neutron star is typically only about 20 kilometers across, but its mass can be greater than that of the Sun. The density is so extreme that a sugar cube-sized chunk of neutron star material would weigh as much as a mountain here on Earth. This immense density leads to gravitational forces so strong that they warp the very fabric of space-time. Additionally, neutron stars rotate at incredible speeds, sometimes completing several hundred rotations every second. This rapid spinning generates beams of radiation that sweep through space like the light of a lighthouse. When these beams point toward Earth, we observe regular pulses of light, known as pulsars. Neutron stars also possess magnetic fields millions of times stronger than Earth's. These powerful magnetic fields generate a variety of emissions, including intense radio waves and other forms of radiation, which can be detected by astronomers. This radiation provides valuable data that allows scientists to learn more about the complex behaviors of these extreme objects. The combination of extreme density, rapid rotation, and powerful magnetic fields makes neutron stars not just fascinating objects in their own right, but also critical to advancing our understanding of the fundamental laws of physics. These stellar remnants are not just the end stage of a star's life, they are the cosmic laboratories that give us a glimpse into the most extreme conditions of matter. When massive stars exhaust their nuclear fuel, they can no longer support themselves against the force of gravity. The core collapses, and in the process, protons and electrons merge to form neutrons, resulting in a neutron star. These stars are far from ordinary. They exhibit extraordinary phenomena, such as their rapid rotation rates, which are the result of the conservation of angular momentum. The collapse causes the star to spin faster, sometimes rotating hundreds of times per second. This rapid rotation, in combination with their immense magnetic fields, produces beams of radiation that sweep across space, creating the pulsar effect. Moreover, neutron stars challenge our understanding of matter. In normal conditions, atoms are the building blocks of matter. However, within a neutron star, the pressure is so high that atoms are compressed to the point where protons and electrons merge to form neutrons. This creates a state of matter unlike anything we encounter on Earth. The layers outside the core of the neutron star may exhibit even stranger properties, potentially harboring exotic particles or even quark matter, further complicating our understanding of these celestial bodies. The behavior of neutron stars also presents puzzles that continue to intrigue scientists. For instance, what drives their rapid spin, and how does it affect their internal structure? The magnetic fields of neutron stars are so powerful that they can trap charged particles, generating beams of radiation that sweep across the sky, offering us another opportunity to study their behavior. These stars serve as valuable testbeds for understanding the fundamental laws of physics, space, and time itself. When two neutron stars collide, the resulting gravitational waves provide us with a unique opportunity to probe the fabric of space-time and deepen our understanding of gravity. Neutron stars, born from the explosive deaths of massive stars, are not just remnants of stellar evolution, they are key to unlocking some of the universe's deepest secrets. Their study holds the promise of revealing the true nature of matter, gravity, and the forces that shape the cosmos. When neutron stars collide, they trigger some of the most powerful and fascinating events in the universe, known as kilonovae. These cataclysmic mergers not only release unimaginable amounts of energy, but also give birth to some of the heaviest elements in existence, like gold and platinum. This revelation opens up a new chapter in understanding the origins of these precious metals throughout the cosmos. Scientists, by studying these dramatic cosmic phenomena and the nature of neutron stars themselves, are able to refine their comprehension of the universe's fundamental laws, gradually unveiling the mysteries of the cosmos in unprecedented ways. Neutron stars, which are the remnants of massive stars that have ended their lives, act as nature's cosmic laboratories. Through these celestial bodies, researchers can gain deep insights into the forces and properties that govern the universe. Each new discovery about the composition and behavior of these dense, compact objects brings us closer to understanding the very structure of reality itself. Binary neutron star mergers, in particular, are events that provide a wealth of information that helps piece together the puzzle of the universe's evolution. A binary neutron star merger occurs when two neutron stars, which are already incredibly dense remnants of collapsed stars, spiral toward each other, drawn by their immense gravitational forces, until they collide with catastrophic force. This event not only produces a spectacular explosion visible across vast distances, but also presents an opportunity for scientists to observe the universe through entirely new means. These mergers release massive amounts of energy, and among the most crucial byproducts are gravitational waves, ripples in the very fabric of space-time itself. The detection of these waves has been groundbreaking, allowing scientists to delve into the very nature of gravity and the fundamental workings of the universe. The detection of gravitational waves from a binary neutron star merger marked a watershed moment in astrophysics. For the first time, we were able to confirm such an event through both gravitational waves and electromagnetic signals, such as visible light, gamma rays, and radio waves. This type of observation, referred to as multi-messenger astronomy, gives astronomers a more complete and nuanced understanding of these cosmic events. It enables them to explore the aftermath of neutron star mergers in unprecedented detail, offering clues that were once impossible to obtain through traditional methods. One of the most exciting outcomes of these cosmic collisions is the creation of heavy elements like gold, platinum, and even uranium. When neutron stars merge, the extreme conditions of pressure and temperature trigger nucleosynthesis, forging these heavy metals and scattering them across space. This not only contributes to the cosmic supply of these valuable elements, but also challenges previously held theories about where such elements originate. The discovery raises fundamental questions about the role these elements play in the formation of planets and life as we know it. By studying the creation and distribution of these elements, scientists are able to refine their models of stellar evolution and better understand how stars, planets, and even life itself may arise from the complex interactions of matter in the universe. The study of binary neutron star mergers has profound implications for understanding the life cycle of stars. These events offer a window into the process of stellar death and rebirth. Understanding the dynamics of neutron stars and the way they merge provides crucial insights into the evolution of the universe itself, including the expansion of the universe and the behavior of dark matter and dark energy, two of the most mysterious components of the cosmos. Far from being mere explosions, these cosmic collisions serve as keys to unlocking the fundamental secrets of the universe. Recent discoveries surrounding neutron stars have revolutionized our understanding of astrophysics. These dense objects, formed when massive stars collapse under their own gravity, are proving to be invaluable laboratories for studying physics under extreme conditions. Neutron stars are so incredibly dense that a single teaspoon of their material would weigh as much as a mountain here on Earth. This immense density allows scientists to probe fundamental questions about the nature of matter, particularly the behavior of particles under extraordinary pressure. Such insights are crucial for refining theories about the fundamental forces that shape the universe. Among the most exciting revelations to emerge from studying neutron stars is the role they play in the creation of heavy elements. When two neutron stars collide, they release vast amounts of energy, leading to the formation of gold, platinum, and other heavy elements. These collisions offer a new perspective on the origins of these elements in the universe, connecting distant cosmic events to the very chemistry that constitutes our world. But that's not all. The detection of gravitational waves during these mergers has opened an entirely new field of study. Gravitational waves are ripples in space-time caused by massive objects accelerating through space. Their detection allows scientists to study events that were once invisible, expanding our understanding of the universe and providing insight into its evolution. Moreover, neutron stars are helping to shed light on the mysteries of dark matter and dark energy, two of the most elusive and poorly understood components of the universe. By studying the interactions of neutron stars and the gravitational waves they emit, researchers are slowly piecing together the puzzle of these enigmatic forces that seem to dominate much of the universe's mass and energy, yet remain largely invisible to us. The recent findings about neutron stars are not just broadening our knowledge of stellar life cycles, they are profoundly influencing multiple areas of astrophysics. From the behavior of matter under extreme conditions to the creation of heavy elements, these discoveries continue to shape our understanding of the universe's evolution. Each breakthrough, no matter how small, propels us closer to solving some of the most profound questions about the cosmos and pushes the boundaries of what we know about the universe and our place within it. The explosive death of a star, known as a supernova, is one of the most spectacular events in the universe. This cataclysmic explosion occurs when a star exhausts its nuclear fuel and can no longer support its own weight. The star's core collapses under gravity, while its outer layers explode outward, creating an immense release of energy. This type of event can occur in two distinct ways, depending on the size and nature of the star involved. The first type of supernova, known as a Type II supernova, happens when a massive star, many times larger than our Sun, reaches the end of its life cycle. Without enough fuel to sustain nuclear fusion in its core, The star collapses and its outer layers are ejected into space in a violent explosion. This explosion is powerful enough to scatter the star's outer layers into the surrounding space at incredible speeds. These ejected materials, rich in heavy elements like carbon, oxygen, and iron, spread throughout the cosmos, enriching the interstellar medium and setting the stage for the formation of new stars and planets. The second type of supernova, called a type Ia supernova, occurs in a binary system where one of the stars is a white dwarf, the remnant of a smaller star that has already undergone a transformation. When the white dwarf accretes material from its companion star, it can reach a critical mass, triggering a runaway nuclear reaction that leads to a violent explosion. Like Type 2 supernova, this explosion sends heavy elements into space, contributing to the cosmic recycling process. Supernovae do more than just mark the end of a star's life. They play crucial roles in shaping the universe. By creating and dispersing heavy elements across space, they contribute to the formation of new stars and planets. Without these cosmic explosions, the elements necessary for life as we know it would not exist. The remnants of some supernovae can even become neutron stars or black holes, depending on the mass of the original star. Thus, supernova act as a catalyst for the continuing evolution of the universe. These explosive events also generate shockwaves that travel through space, compressing nearby gas and dust, which triggers formation of new stars. This process, known as stellar nucleosynthesis, is akin to a cosmic chain reaction, where the death of one generation of stars leads to the birth of the next. In this way, the cycle of stellar life and death continues to shape the universe, creating a dynamic and ever-evolving cosmos. Supernovae, some of the most dramatic and powerful explosions in the universe, are critical events that profoundly influence the cosmos in ways that extend far beyond the moment of their eruption. These colossal explosions, marking the death of massive stars, release vast amounts of energy and matter into space. The immense radiation generated by a supernova can have lasting effects on nearby celestial bodies, potentially altering the climate or even stripping away the atmosphere of planets in close proximity. This process can create conditions that either hinder the development of life or, conversely, pave the way for new forms of cosmic evolution. Supernovae play a pivotal role in the grand cosmic ecosystem. They are not merely destructive events, they are also creative forces. By expelling vast amounts of matter into space, they provide essential elements that are necessary for the formation of new stars and planetary systems. The elements released during a supernova, including carbon, oxygen, iron, and many others, are heavier than the hydrogen and helium that predominated in the universe's early stages. These elements are vital for building the next generation of stars and planets, as well as the complex structures that emerge within galaxies. When a massive star exhausts its nuclear fuel, it can no longer maintain the balance between the inward pull of gravity and the outward pressure generated by nuclear fusion. Unable to support its own weight, the star collapses under the force of its own gravity, triggering a catastrophic explosion. This explosion, a supernova, ejects the star's outer layers into space in a spectacular display of energy and light. The force of the explosion is so intense that it sends shock waves through the surrounding gas and dust, compressing these materials and triggering the birth of new stars in nearby regions. The energy released during a supernova also has far-reaching consequences. It can influence the structure of entire galaxies. The shock waves from the explosion can create disturbances in the interstellar medium, the gas and dust that exist between stars, leading to the formation of new star clusters or influencing the dynamics of the galaxy itself. These energetic explosions are not just fleeting moments of destruction. They set in motion a cosmic dance of creation and annihilation, shaping the very environment in which galaxies evolve. In the aftermath of a supernova, the elements scattered into space contribute to the chemical enrichment of the universe. New stars, formed from the remnants of these earlier explosions, inherit these elements, and when they eventually die, they too may explode, continuing the cycle of creation and dispersal that drives the evolution of the cosmos. Through this process, supernovae ensure that the universe is constantly replenished with the raw materials needed for star formation, the creation of planetary systems, and the development of more complex structures within galaxies. Supernovae also offer profound insights into the life cycle of stars. By observing and studying these explosive events, astronomers can piece together the processes that lead to stellar death. There are two primary types of supernova: core collapse supernova, which occur when massive stars run out of fuel and collapse under their own gravity, and type 1a supernova, which arise from binary systems in which a white dwarf accumulates material from a companion star until an explosion occurs. Each type of supernova has its own distinctive characteristics, and studying them deepens our understanding of stellar evolution. One of the most intriguing aspects of supernovae is their role in the study of the universe's expansion. In the late 20th century, scientists discovered that certain types of supernovae, particularly type 1a, appeared dimmer than expected when observed at great distances. This dimming suggests that these objects are farther away than previously thought, implying that the universe's expansion is accelerating. This unexpected finding led to the groundbreaking discovery of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Supernovae also play a crucial role in the formation of the heavy elements that populate the universe. When these massive stars explode, they forge elements like iron, gold, uranium, and others in the intense heat and pressure of the explosion. These elements are then scattered across space, enriching the material in interstellar clouds. Over time, this enriched material will contribute to the formation of new stars and planets, including our own. Essentially, every atom in our bodies likely originated in the heart of a star that exploded long before the Earth came into existence. Moreover, supernovae act as natural laboratories for scientists. By studying these explosions, researchers can learn about the life cycles of stars, the chemical evolution of the universe, and the mysteries of cosmic expansion. The energy released by a supernova is so immense that it can briefly outshine an entire galaxy, providing astronomers with the opportunity to study these events from vast distances. Each supernova is a treasure trove of data, helping to shape our understanding of the universe. Despite their importance, many aspects of supernovae remain shrouded in mystery. For instance, while the basic process of a supernova is understood, the exact mechanisms behind these colossal explosions are still not fully known. There are various types of supernovae, and unraveling the precise conditions that lead to each one remains a challenge. Some supernovae arise from the collapse of massive stars, while others occur in binary systems, where one star siphons material from its companion until an explosion is triggered. Understanding these processes is crucial for gaining a deeper insight into stellar life cycles and the dynamics of star systems. Another area of active research is the creation and distribution of the elements produced during a supernova. Supernovae are responsible for forming many of the heavy elements, such as gold and uranium that we observe in the universe today. Scientists are eager to understand how these elements are created, how they are distributed across space, and how this process contributes to the formation of planets and life itself. By studying the distribution of these elements, scientists can piece together the history of our galaxy and the broader universe. Supernovae are not only vital to the continued evolution of the universe, but they also serve as a reminder of the dynamic and ever-changing nature of the cosmos. Their explosive deaths generate the very building blocks from which new stars and planets are born, ensuring that the cycle of creation and destruction continues, shaping the future of the universe for eons to come. Through the study of these stellar explosions, scientists are constantly uncovering new insights into the forces that drive the cosmos, making supernovae one of the most fascinating and important phenomena in modern astrophysics. Furthermore, there exists the enigmatic phenomenon of dark energy, whose complex and mysterious nature continues to intrigue researchers, especially when viewed through the lens of supernovae. Supernovae, as cosmic explosions of dying stars, play an essential role in helping scientists measure and understand the vast stretches of space. In particular, observations of distant supernovae have revealed a groundbreaking discovery. The universe is not just expanding, but it is expanding at an accelerating rate. This revelation, which has reshaped our understanding of the cosmos, has prompted a surge in scientific inquiry into the true nature of dark energy. the force believed to be driving this accelerated expansion. Scientists are now intent on uncovering how these supernovae can serve as precise markers for measuring cosmic distances, offering insights not just into the past and present state of the universe, but also into its potential fate. In addition to shedding light on the broader dynamics of cosmic expansion, supernova remnants, the scattered material left in the wake of these explosive events, offer scientists a glimpse into the earliest stages of the universe. These remnants, often seen as the aftermath of stellar deaths, function as natural laboratories, offering critical data on the processes that led to the formation of new stars, galaxies, and even the elements necessary for life. The study of these remnants is thus far from being a simple exploration of the final stages of a star's life. Rather, it opens up profound questions about the very nature of cosmic evolution, from the elemental compositions produced in these explosions to the mechanisms governing star formation and galaxy evolution. Supernovae reveal the intricate processes at work in the universe's ever-changing landscape. As researchers continue to study supernova, the broader implications of their discoveries touch upon several pivotal areas of astrophysical research. These areas range from the life cycle of stars and the creation of heavy elements to the fundamental mysteries surrounding the universe's expansion and ultimate destiny. Every new piece of information gleaned from the study of supernovae and their remnants serves to unravel yet another layer of the universe's most profound mysteries, drawing us ever closer to a deeper understanding of the forces that shape the cosmos. Yet, one of the most profound and perplexing aspects of the universe is not solely found in the visible matter, such as galaxies and stars, but in the vast, empty spaces that stretch between them. These cosmic voids, enormous regions where very few galaxies can be found, represent a major frontier in cosmological research. To visualize this, think of the universe as an immense sponge. The galaxies and galaxy clusters are the dense, compact sections of matter that make up the sponge's structure, while the empty voids are the vast, nearly barren spaces that separate them. These voids are not mere gaps. They are enormous in scale, some spanning hundreds of millions of light years across, and they provide astronomers with an unparalleled opportunity to study the universe's large-scale structure without interference from densely packed regions of galaxies. The existence of these voids plays a critical role in our understanding of the universe's overall evolution. As the universe continues to expand, the voids themselves are growing ever larger. This phenomenon occurs because gravity pulls matter, such as galaxies, toward each other, leaving the vast, empty spaces increasingly devoid of substance. Studying these voids provides astronomers with valuable insights into dark energy, the mysterious force believed to be responsible for the accelerated expansion of the universe. By examining regions with few galaxies, scientists can analyze the cosmos on a grand scale, helping to unravel the role dark energy plays in shaping the universe's continued expansion. The study of cosmic voids also highlights their importance as fundamental structures within the greater cosmic framework. Though these voids may appear empty, they are not entirely devoid of matter. Instead, they can contain small amounts of dark matter and gas, though at much lower densities than the galaxies or clusters that surround them. Over time, researchers have discovered that these voids can be far larger than initially thought. In some cases, they span vast stretches of space, influencing the motion of galaxies in their vicinity. This discovery challenges previous models that assumed a more uniform distribution of matter and forces scientists to rethink the intricate balance between matter, gravity, and dark energy. Interestingly, cosmic voids are not uniform in size or shape. Some voids are enormous, stretching across millions of light years, while others are smaller but still significant in size. The shape of these voids often tends to be more elongated than spherical, with some scientific theories suggesting that this characteristic might reflect the conditions of the universe shortly after the Big Bang. In the aftermath of the Big Bang, gravity caused matter to clump together, forming clusters of galaxies, while the regions with lower densities became the voids that we observe today. The varying sizes and shapes of these voids are thought to be influenced by the distribution of dark matter, an invisible substance that makes up much of the universe's mass but cannot be directly observed. This unseen matter plays a crucial role in shaping how voids evolve over time, guiding the gravitational pull and distribution of cosmic material. As scientists continue to investigate the evolution of these voids, they are uncovering their impact on the formation and development of galaxies. In areas near voids, galaxies are more likely to interact with one another, leading to complex mergers and the formation of new galactic structures. In contrast, the emptiness of a void may have less impact on galaxy formation, with fewer galaxies taking shape in these isolated regions. This creates a unique environment that influences the life cycles of galaxies, affecting how they grow, evolve, and eventually reach the end of their existence. Additionally, the study of cosmic voids offers valuable insights into the fundamental forces at play in the universe. For instance, the cosmic microwave background, CMB, the afterglow of the Big Bang, contains patterns that are linked to the formation of these voids. By examining these patterns, scientists can gain a deeper understanding of the nature and amount of dark energy, a force that is still poorly understood, but plays a critical role in the universe's accelerating expansion. In this way, cosmic voids are far from being mere gaps in space. They are active participants in the cosmic story, offering key clues about the universe's past, present, and future. In fact, cosmic voids are a fundamental aspect of the universe's large-scale structure. As scientists continue to study these vast emptinesses, they are uncovering new dimensions to our understanding of gravity, dark matter, and dark energy. These voids challenge our traditional models of the universe and force us to rethink our assumptions about the distribution of matter and the forces that govern cosmic evolution. They are not just empty spaces. They are dynamic regions that play an essential role in shaping the overall structure of the cosmos. The existence of cosmic voids fundamentally challenges our understanding of the universe's large-scale structure. These voids, which occupy a significant portion of the cosmos, suggest that the distribution of matter is far more complex than previously believed. Rather than being a smooth, uniform spread of galaxies and matter, the universe is a vast, interconnected web of galaxies and voids, with the galaxies clinging to the threads of a cosmic web while the voids fill the spaces in between. This revelation has forced scientists to reevaluate many of their long-held beliefs about the formation and evolution of the universe, as these voids pose new questions about the forces that have shaped the cosmos over billions of years. In conclusion, cosmic voids are not mere empty spaces in the universe. They are dynamic, integral components of the cosmic structure. Their study is crucial to our understanding of the universe's evolution, the distribution of dark matter, and the mysteries of dark energy. These voids challenge existing models and push the boundaries of scientific knowledge, offering profound insights into the very fabric of the universe and its complex, interconnected web of matter and energy. The existence of cosmic voids, vast and seemingly empty spaces scattered throughout the universe, plays a crucial role in enhancing our understanding of cosmic expansion. These voids are not merely empty gaps between celestial bodies. They are integral to the story of the universe's evolution. The universe, continually expanding, stretches out over time, and with it, the voids themselves grow. By studying the growth of these voids, scientists can unlock valuable information about the forces driving the universe's accelerated expansion, particularly the enigmatic force known as dark energy. Dark energy is thought to be the driving force behind this acceleration, and understanding the behavior of cosmic voids offers a window into how this mysterious entity influences the universe. Furthermore, delving into the formation of voids provides important clues about the early conditions of the universe. These voids were born out of the density fluctuations that occurred following the Big Bang, serving as markers of the uneven distribution of matter in the universe's infancy. By analyzing how these fluctuations gave rise to the vast, empty spaces, researchers can piece together a more detailed picture of the universe's initial state and the forces that shaped its growth. This in turn helps scientists refine their understanding of the universe's structure from its formation through the current era, and allows them to challenge and enhance existing cosmological theories. Contrary to their name, voids are not mere emptiness. They are active players in the grand cosmic narrative, shaping the very fabric of the universe. By studying them, we begin to see how they influence the development of galaxies, the distribution of dark matter, and the fundamental forces that drive the universe's evolution. With each new discovery, the significance of cosmic voids becomes ever clearer, providing a deeper connection to the cosmos and revealing the complexities hidden within the universe's expansive web. Superclusters are another awe-inspiring feature of the universe. These colossal formations consist of numerous galaxy clusters, which themselves are massive collections of millions of stars, planets, and other celestial bodies. To grasp this concept, imagine a neighborhood filled with houses, each house representing a galaxy. The neighborhood, in turn, represents a galaxy cluster. Now, visualize several of these neighborhoods coming together to form a larger community. That larger community is a supercluster. The scale of superclusters is mind-boggling. While a typical galaxy cluster might span tens of millions of light years, superclusters can extend over hundreds of millions or even billions of light years. This means that a supercluster can contain hundreds or even thousands of galaxy clusters within its vast expanse. This immense scale fundamentally alters how we perceive the structure of the universe. Superclusters form a vast, interconnected web of galaxies and clusters, creating a grand cosmic architecture that underpins the universe's organization. Superclusters, however, are not evenly distributed across space. Instead, they are aligned along vast filaments of galaxies, forming the backbone of the universe's large-scale structure. This arrangement arises from the fundamental force of gravity, which pulls matter together in an intricate cosmic dance. In between these superclusters lie vast expanses of emptiness, the cosmic voids, further emphasizing the contrast between the densely populated regions and the uninhabited areas. The study of superclusters offers astronomers the opportunity to better understand the universe's formation, its ongoing expansion, and the distribution of dark matter, a still mysterious substance that makes up the majority of the universe's mass. Superclusters represent the largest known structures in the cosmos, surpassing even the size and complexity of individual galaxy clusters. By investigating these massive structures, scientists gain insight into the broader framework of the universe, revealing the interconnectedness of galaxies and clusters and how they have evolved over cosmic timescales. Superclusters, like cosmic voids, are not passive structures. They actively shape the behavior of the universe, particularly the formation of galaxies and the distribution of dark matter. The study of these structures begins with mapping their locations across the sky. By utilizing powerful telescopes equipped with advanced imaging technologies, scientists are able to capture the light emitted by the galaxies within superclusters. This light provides crucial information about the composition and behavior of these galaxies, as well as their movements and interactions with one another. The light from distant galaxies, observed in different wavelengths, can reveal much about their internal processes. For example, the rate at which galaxies are forming stars, or the types of gases that make up their composition, offers clues to how superclusters influence their surroundings. Additionally, the study of how superclusters affect the flow of matter and energy in the universe can shed light on the behavior of dark matter, a substance that remains invisible to conventional telescopes, but is essential to the structure of the cosmos. To deepen our understanding of superclusters, scientists also rely on simulations, computer models that replicate the development of the universe over billions of years. By simulating the formation of superclusters, researchers can study how these massive structures grow and interact with other cosmic phenomena, such as the vast voids. These simulations provide a powerful tool for testing hypotheses about the universe's evolution, complementing observational data to refine our understanding of cosmic growth. One of the most profound sources of information about the universe comes from the cosmic microwave background radiation, CMB. This faint afterglow of the Big Bang carries crucial clues about the early state of the universe, including the distribution of matter shortly after its inception. Variations in the CMB reflect the density fluctuations that occurred in the universe's infancy, laying the groundwork for the formation of structures such as superclusters. By studying these fluctuations, scientists can trace the origins of superclusters, providing further insight into their role in shaping the universe's architecture. In addition to the direct study of superclusters, scientists are also exploring their relationship to the broader cosmos. Superclusters, as the largest known structures in the universe, offer an unprecedented view into how the universe is organized. Their immense gravitational influence affects the movement of galaxies, bending light in a phenomenon known as gravitational lensing. This effect distorts the light from more distant objects, acting like a cosmic magnifying glass. By studying these distortions, scientists can map the distribution of dark matter, an invisible yet crucial component of the universe's mass, and gain insight into its role in shaping cosmic structures. Superclusters serve as cosmic puzzles that challenge our understanding of both visible and invisible forces in the universe. They push researchers to rethink fundamental principles, such as the nature of gravity and the elusive characteristics of dark matter. By unraveling the mysteries of these vast structures, scientists gain new perspectives on how the universe operates and evolve their understanding of the forces that shape it. The distribution of superclusters across the universe follows a web-like structure, with dense clusters connected by vast, more sparsely populated regions. These superclusters are not just collections of galaxies, they influence the formation and movement of galaxies within them. When galaxies are located close to one another in a supercluster, they interact and share resources like gas and dark matter, fostering the conditions for star formation. This interaction can lead to the creation of new suns and potentially new planets, vital ingredients for life as we know it. The gravitational pull of superclusters also has a profound effect on galaxy motion. Acting as gravitational lenses, superclusters bend light from distant galaxies and alter the way we observe the universe, revealing information about the unseen mass that holds the cosmos together. The locations and distribution of superclusters offer more than just insights into the current state of the universe. They also provide valuable information about its past and future. By studying the arrangement and density of these superclusters, scientists can infer the expansion rate of the universe and better understand the forces driving its ongoing evolution. The distribution of superclusters serves as a cosmic map, helping researchers understand how the universe is growing and changing, much like how the growth patterns of a plant reveal the conditions around it. In essence, superclusters are not just structures in the universe, they are dynamic forces shaping the universe's development. Their study provides a deeper understanding of the forces that influence galaxy formation, the distribution of dark matter, and the very nature of the cosmos. The more we uncover about superclusters, the more we unlock the mysteries of the universe itself. Recent advancements in observational technology have significantly enhanced our ability to study these superstructures. With powerful telescopes and cutting-edge imaging techniques, astronomers can now capture detailed data from deep space. This allows researchers to map the distribution of galaxies, dark matter, and other cosmic structures, revealing how they are interconnected. The resulting map resembles a vast cosmic spiderweb, with galaxies linked together by gravity, forming intricate patterns across the universe. These observations help scientists understand not only the locations of galaxies, but also how they interact with one another and with the gravitational pull of superclusters. The study of these superstructures continues to deepen our understanding of the universe, offering new insights into the very nature of reality itself. Over time, advancements in observational techniques have significantly enhanced our ability to study the cosmic background radiation at the ancient light left over from the Big Bang. This faint radiation carries invaluable information about the early universe and offers us an extraordinary window into the past. By analyzing this radiation, scientists can uncover critical details about how the universe began to form, providing insight into the development of superstructures over cosmic time. These insights reveal how regions of higher and lower density emerged, laying the groundwork for the grand cosmic architecture we observe today. Through this cosmic detective work, astronomers can infer how galaxies, clusters of galaxies, and even larger structures came to be. This process helps us understand not only the formation of the universe's large-scale structure, but also how dark energy, the mysterious force accelerating the expansion of the universe, plays a role. Dark energy's influence has become one of the most intriguing aspects of modern cosmology. As scientists piece together the behaviors of these superstructures in relation to dark energy, they gain clues about the universe's ultimate fate. These observations also challenge our understanding of gravity, time, and the forces that govern the cosmos. As we peer deeper into the distant reaches of space, each discovery adds another layer to our comprehension of this grand narrative. We are constantly unraveling the profound mysteries of the universe, which seem to expand endlessly before us, offering more questions than answers. The mysteries of space continue to captivate, inviting new generations of astronomers and physicists to explore what is beyond our reach. In the realm of theoretical physics, wormholes stand as one of the most tantalizing and speculative concepts. These hypothetical structures, which scientists believe might exist in the fabric of space-time, offer the possibility of shortcuts across vast distances. Imagine space-time as a vast, flexible sheet that stretches across the universe. If two distant points on this sheet could be folded together, a direct pathway, or wormhole, could be created between them. This concept imagines that instead of traveling across the vast expanse of space, one could simply take a shortcut through the fabric of space-time, reducing what would normally be a long, arduous journey to an instant traversal. The beauty of a wormhole lies in its potential to revolutionize how we move across the universe. Imagine journeying from one star system to another, bypassing the enormous distances that would otherwise take thousands of years to cross. In the theory of general relativity, Einstein's equations suggest that such shortcuts are mathematically possible. However, it is important to note that wormholes remain purely theoretical. No empirical evidence has yet confirmed their existence. One of the most significant challenges in understanding wormholes is their stability. Many scientists hypothesize that these structures might be inherently unstable. Without the presence of exotic matter, a theoretical substance with negative energy density, a wormhole might collapse before anything could pass through it. Exotic matter would be required to keep the tunnel open, but such matter has yet to be discovered. Thus, we remain in a realm of speculation, with wormholes serving as a fascinating yet unproven idea. Moreover, if wormholes do exist, they could potentially introduce all kinds of bizarre and unsettling scenarios. Crossing a wormhole might expose travelers to intense gravitational forces, extreme radiation, or even unknown phenomena that we cannot yet predict. This raises the question of whether wormhole travel would be safe or feasible. Would we be able to navigate such an environment, or would the very fabric of our bodies and equipment be destroyed by the stresses involved? The concept of wormholes is deeply intertwined with Einstein's theory of general relativity. According to this theory, massive objects like stars and black holes warp the fabric of space-time around them, creating what we experience as gravity. General relativity also provides the theoretical framework for wormholes, suggesting that if space-time could be bent sufficiently, two distant points could be connected by a tunnel. This theoretical tunnel would allow for instantaneous travel across what would otherwise be unreachable distances. Beyond Einstein's work, other fields of theoretical physics, including quantum mechanics and string theory, have expanded on the idea of wormholes. These theories propose that the universe may have hidden dimensions and properties, opening the door to new ways in which wormholes could exist and function. Some theories even suggest that wormholes could be gateways to parallel universes or alternate realities. Yet, despite these captivating possibilities, the existence of wormholes remains entirely speculative. Without concrete experimental evidence, they remain a part of the theoretical landscape. To bring the concept of wormholes to life, think of space-time as a sheet of paper. When you place a heavy object on the paper, the sheet bends under its weight. If you could fold the paper so that two distant points touch, you would create a shortcut between them. In the universe, this would mean connecting two far-flung locations with a direct path. This is the essence of how wormholes are theorized to work, bending the very fabric of space and time to form shortcuts between distant regions of the cosmos. Despite the allure of wormholes, the reality of traveling through them presents a host of challenges. First, the very existence of wormholes is still unproven. While solutions to Einstein's equations suggest their theoretical possibility, no one has yet observed one in nature. Even if wormholes do exist, many believe that they would be highly unstable, collapsing almost immediately without the stabilizing influence of exotic matter. The very nature of their existence would require materials and forces that we have yet to discover. Even if a stable wormhole could be created, there are other significant hurdles. Traveling through a wormhole could expose passengers to severe gravitational forces and high-energy radiation, both of which could be harmful. Navigating a wormhole would require technology far beyond what we currently possess, as our space vehicles are not yet capable of withstanding the unknown stresses such a journey would involve. The potential for catastrophic failure would make even the idea of wormhole travel a daunting challenge. Moreover, the implications of wormhole travel challenge our understanding of causality, the fundamental relationship between cause and effect. If we could instantly travel to distant parts of the universe, could we also travel back in time? Would that allow us to alter the past and create paradoxes that disrupt the very fabric of reality? These questions highlight the deep philosophical and scientific challenges that wormhole travel would pose. Even with these considerable uncertainties, the idea of wormholes captures the imagination. If they could be stabilized and traversed safely, they would revolutionize space travel. Imagine being able to visit distant stars and galaxies in a fraction of the time it would normally take, or sending messages and materials across the universe as easily as we send information over the internet today. Such advancements could reshape the way we think about exploration, communication, and the very nature of the cosmos itself. In the end, wormholes remain a fascinating and highly speculative concept. While they hold the potential to transform space travel and communication, many hurdles remain before they could become a reality. Nevertheless, the idea that the universe might have hidden shortcuts waiting to be discovered continues to inspire scientific inquiry and fuel our curiosity about the cosmos. Each new exploration of this idea adds another layer to the rich tapestry of human understanding about the universe and our place within it. However, these advancements come with significant challenges that cannot be ignored. While theoretical concepts offer a captivating glimpse into what could be possible, the practical application of these ideas remains elusive. We still face numerous hurdles in understanding how to create, stabilize, and navigate such complex structures safely. The exploration of space-time, gravity, and quantum mechanics, though advancing, requires ongoing research to bring these theories closer to reality. If successful, research into wormholes could revolutionize space travel, enabling us to reach distant stars far quicker than ever before. It could also reshape humanity's perception of our place in the universe, offering new perspectives on what we once thought impossible. Yet, even as the idea of traversing vast distances in the blink of an eye tantalizes us, the hard work of making it a reality continues. At the heart of these cosmic endeavors lies the study of cosmic rays, high-energy particles that travel through space, originating from a variety of sources beyond our atmosphere. Imagine them as minuscule, charged bullets streaking across the vast expanse of the universe, carrying secrets that could unlock profound truths about the cosmos. These particles are primarily composed of protons, the positively charged particles found in atomic nuclei. However, cosmic rays can also include heavier atomic nuclei and even some electrons, making them even more intriguing to scientists. What makes cosmic rays particularly fascinating is their origin. They come from some of the most extreme and powerful phenomena in the universe: exploding stars, supernova, and even the sun itself. When cosmic rays enter Earth's atmosphere, they don't just pass through unnoticed. Instead, they interact with the gases in the air, producing a cascade of secondary particles. This is akin to throwing a stone into a calm pond and watching the ripples spread outward. Similarly, when a cosmic ray strikes an atom in the atmosphere, it can trigger a surge of new particles, including muons and neutrinos. This chain reaction leads to the creation of a shower of particles, which is how scientists can detect cosmic rays. The interactions of cosmic rays don't just provide us with a means of detection, they offer valuable insights into some of the most extreme environments in the universe. Studying these particles helps scientists gain a deeper understanding of the conditions near black holes, within supernova explosions, and other high-energy cosmic events. Some cosmic rays even carry detailed information about their sources, revealing clues about how stars form, evolve, and ultimately die. This information is crucial for understanding the life cycles of stars and the broader dynamics of the universe. Despite their fascinating nature, cosmic rays also present challenges for space exploration. Over extended periods, cosmic rays pose a significant risk to astronauts, as their high-energy collisions can damage spacecraft and cause radiation exposure. Protecting astronauts from these particles is one of the many hurdles that need to be overcome as we look toward longer-duration space missions. In essence, cosmic rays are more than just fast-moving particles. They are messengers from the universe itself. Each ray carries with it a snapshot of the processes that govern the cosmos. Yet their study reveals a complex interplay of interactions that shape the space around us. The way these particles behave when they collide with Earth's atmosphere provides not just a window into their origins, but also a deeper understanding of the universe's fundamental workings. Detecting and measuring cosmic rays is no simple task. It requires a combination of sophisticated technology and intricate networks of instruments. There are various methods used to capture these particles, each offering different insights into their properties. One common approach involves ground-based detectors. These devices are scattered across vast fields, carefully positioned to sense the secondary particles produced when cosmic rays collide with the atmosphere. The detectors are often arranged in large arrays, allowing them to identify the energy levels and trajectories of the particles that reach the ground. By analyzing data from many of these events over time, scientists can infer the energy and direction of the original cosmic rays, providing a clearer understanding of their origins. Another method involves space-based observatories, which are designed to measure cosmic rays before they even reach Earth's atmosphere. Satellites and instruments aboard spacecraft, such as those on the International Space Station, are equipped to detect cosmic rays as they travel through space. These instruments measure the energy and type of particles, offering invaluable information about their behavior and their cosmic origins. Furthermore, specialized materials such as thick layers of water or ice are sometimes used to observe the secondary particles created by cosmic ray collisions. By studying how far these secondary particles travel and how much energy they lose before being detected, researchers can learn more about the properties of the original cosmic rays. This combination of technologies allows scientists to not only measure cosmic rays, but also understand the environments and processes that generate them, whether that be supernovae, active black holes, or other energetic cosmic phenomena. Through continuous monitoring and data collection, researchers are steadily building a more comprehensive picture of these elusive cosmic travelers. The role cosmic rays play in the broader cosmos is becoming clearer with each new discovery, and with every new data point, our understanding of the universe's most extreme events deepens. Cosmic rays are high-energy particles that bombard Earth from every corner of the universe. Their origins are shrouded in mystery, as scientists continue to explore where these particles come from and what they are made of. Most cosmic rays are composed of protons, particles that make up atomic nuclei. However, they can also include heavier particles, like helium nuclei, as well as a variety of other atomic fragments. Understanding the precise origins of cosmic rays is one of the great challenges in modern astrophysics. Some cosmic rays are believed to originate from our sun, especially during solar flares, while others are thought to come from far more powerful sources, exploding stars known as supernovae, and even the eruptions of black holes. However, pinpointing the exact source of many cosmic rays remains an elusive task. These particles travel vast distances through the galaxy, and as they do, they can be deflected by magnetic fields, making it extremely difficult to trace them back to their source. Furthermore, the energies of some cosmic rays are so high that they defy our current understanding of physics. Some cosmic rays possess energy levels that surpass those of particles produced in even the most powerful human-made particle accelerators. This raises an intriguing question. What kind of astronomical phenomena could produce such powerful particles? Investigating the sources of these cosmic rays could provide crucial insights into some of the universe's most energetic and enigmatic events. Moreover, scientists are studying the composition of cosmic rays to better understand their behavior. While most cosmic rays are protons, the presence of heavier atomic nuclei suggests that these particles undergo complex interactions. Cosmic rays may collide with other particles in space, gaining energy and changing their form as they travel. This process of transformation offers valuable clues about the nature of the particles and the events that produce them. Research into cosmic rays is not just about understanding the particles themselves, it also provides key insights into fundamental questions about matter, energy, and the very nature of the universe. By continuing to explore the origins and characteristics of cosmic rays, researchers are unlocking the mysteries of high-energy processes in the cosmos. These studies could ultimately lead to a better understanding of the universe's most powerful forces and provide answers to questions that have long eluded us. Cosmic rays are a fascinating phenomenon, offering an unparalleled window into the high-energy processes of the universe. These particles, which originate from distant regions of space, provide us with insights into the fundamental nature of matter and energy. On Earth, we can observe the interactions between cosmic rays and the atmosphere, helping us understand the conditions under which these particles travel and the events that produce them. While particle accelerators on Earth allow scientists to recreate high-energy collisions, cosmic rays naturally achieve even higher energies as they interact with particles in the atmosphere. By studying the particles produced from these collisions, scientists can learn about interactions that are otherwise impossible to replicate in a lab setting. Additionally, investigating cosmic rays helps us understand the sources of these high-energy particles. They are believed to be generated by some of the most powerful events in the universe, such as supernovae, neutron star mergers, and black hole eruptions. These events release vast amounts of energy, and by studying them, we gain deeper insights into the cosmic processes that govern the universe. Each discovery brings us closer to understanding the forces that shape the universe itself, offering not only a glimpse into the unknown, but also revealing the fundamental mechanics of the cosmos. Cosmic rays are among the most enigmatic and intriguing phenomena in the universe, playing an essential role in unraveling the very structure and origins of the cosmos. These high-energy particles, which constantly bombard the Earth from all directions, carry with them invaluable information about the fundamental forces and building blocks of the universe. They are key to understanding the properties of subatomic particles like protons and neutrons, influencing theories about dark matter and offering new insights into the expansion of the universe. By probing these cosmic messengers, scientists hope to push the limits of our knowledge, unveiling aspects of the universe that are otherwise hidden from view. At their core, cosmic rays offer a natural laboratory for exploring high-energy physics. They reveal interactions between particles and forces at scales and energies far beyond the reach of traditional Earth experiments. Their study deepens our understanding of the universe and sheds light on the forces that govern it, from gravity to electromagnetism. As research into cosmic rays continues, it promises to expand our knowledge in unexpected ways, particularly in relation to the origins and effects of these particles in the larger context of the universe. One of the most pressing questions in cosmic ray research is where these high-energy particles originate. Some scientists hypothesize that they may be produced by the explosive death of stars, such as in supernova explosions, or by the intense gravitational forces around massive black holes. However, pinpointing the exact sources of these particles is no simple task, as the conditions that produce them are extreme and difficult to replicate. To tackle this challenge, a variety of new observatories and detection systems are being built across the globe. These projects are equipping scientists with the tools to look deeper into the universe than ever before. Among the cutting-edge tools being developed are vast arrays of sensors capable of detecting the faint flashes of light produced when cosmic rays collide with the Earth's atmosphere. By analyzing these interactions, researchers can glean information about the energy, direction, and source of the cosmic rays. Tracking these particles back to their origins will provide crucial insights into the most extreme astrophysical events in the universe, from supernovae to black hole accretion disks. Space-based experiments are also set to revolutionize our understanding of cosmic rays. Unlike Earth-based detectors, which are distorted by the atmosphere, satellites equipped with specialized instruments will enable scientists to observe cosmic rays without interference. These space missions will map the energy spectrum of cosmic rays, helping researchers understand their composition, behavior, and how they travel across vast stretches of space. By studying cosmic rays in their natural, undistorted state, scientists will be able to piece together a more complete picture of the forces shaping the universe. In addition to their astrophysical significance, cosmic rays may also hold answers to questions in Earth science. Researchers are exploring how these high-energy particles interact with the atmosphere and whether they might have any long-term effects on weather patterns. This represents an intriguing intersection between the fields of astrophysics and earth sciences, where the study of cosmic rays could provide new insights into the impact of space weather on our planet's systems. Through these multifaceted approaches, the scientific community hopes to unravel the mysteries of cosmic rays, each discovery offering a step closer to understanding the fundamental workings of our universe. Amidst the search for answers to these cosmic mysteries, one of the most fascinating objects in the universe is the magnetar, a highly magnetic type of neutron star. These stellar remnants, which are born from the explosive deaths of massive stars, are some of the most extreme and exotic objects in the cosmos. A neutron star in its basic form is already a dense, compact object with more mass than the Sun packed into a sphere just a few kilometers across. However, a magnetar takes this density to the extreme, combining it with the most powerful magnetic field known to exist in the universe. These fields can be 1,000 billion times stronger than Earth's, influencing everything around them in extraordinary ways. Magnetars are characterized not only by their intense gravitational pull, but also by the tremendous energy they emit. One of the most striking phenomena associated with magnetars is their ability to produce bursts of high-energy radiation. These bursts can be millions of times more powerful than the radiation emitted by typical neutron stars, and they occur in the form of gamma rays, one of the most energetic forms of light in the universe. These gamma ray emissions can be detected over vast distances, allowing scientists to study magnetars even when they are located far from Earth. What truly sets magnetars apart, however, is the impact of their magnetic fields on their surroundings. The strength of their magnetic forces is so immense that they can alter the behavior of charged particles in the vicinity, causing them to spiral and accelerate along the magnetic field lines. This movement generates high-energy radiation, including X-rays and gamma rays. These intense bursts of energy are not just limited to radiation, they can also cause the crust of the neutron star itself to crack and shift. This phenomenon, known as a magnetar flare, releases enormous amounts of energy in a brief but intense burst. These flares are some of the most powerful explosions in the universe, capable of generating shock waves that ripple through space, and even reaching Earth. Another intriguing aspect of magnetars is their magnetic field decay. Over time, the strength of the magnetic field weakens, causing the star's activity to decrease. This gradual decline in energy production is part of the magnetar's life cycle, leading to periods of reduced activity and potentially a transition into a more passive state, resembling a typical neutron star. Despite this decline, the effects of magnetar flares can continue to be observed long after the star has lost much of its magnetic energy. The life of a magnetar is both brief and intense, especially when measured in cosmic terms. While neutron stars can persist for millions of years, the active phase of a magnetar typically lasts only a few thousand to a few 100,000 years. This relatively short lifespan is due to the rapid depletion of its magnetic energy, which eventually causes the star to become less active and fade into obscurity. Yet, even as their energy fades, magnetars continue to offer unique glimpses into the extreme laws of physics that govern the universe. The formation of magnetars is closely tied to the dramatic death of massive stars. When such a star runs out of nuclear fuel, it undergoes a catastrophic collapse under its own gravity, compressing the core to densities so high that the resulting neutron star can exhibit magnetic fields millions or even trillions of times stronger than Earth's. These magnetic fields are not static. They can grow stronger over time due to the extreme pressure and rapid rotation of the neutron star. As the magnetic field decays, it releases powerful radiation in the form of X-rays and gamma rays, which are detected as flares. Magnetars are born from the violent deaths of stars, where gravitational forces and magnetic fields combine to create one of the most powerful and extreme objects in the universe. Their lifetimes may be short compared to other stellar remnants, but during their active phase, they provide unparalleled opportunities to study the interplay between magnetic fields, gravity, and radiation. As researchers continue to probe these mysterious objects, each new discovery brings us closer to understanding the complex forces that shape the universe and the extraordinary phenomena that arise from them. Magnetars represent a fascinating and complex phase in the evolution of stars, revealing a process that goes far beyond traditional expectations. These enigmatic celestial objects are characterized by magnetic fields that are trillions of times stronger than Earth's own magnetic field. Such extraordinary magnetic strength results in highly energetic bursts of radiation, including X-rays and gamma rays, which not only illuminate their surroundings, but also provide scientists with invaluable insights into their nature. These powerful bursts are a signature feature of magnetars, and they allow researchers to probe deeper into the mechanisms at play in these extreme environments. The magnetic fields of magnetars are believed to originate from the rapid rotation and collapse of massive stars, a process that suggests that the death of a star may result in far more than just a simple neutron star. While most neutron stars are thought to gradually cool and fade away over time, magnetars challenge this idea, indicating that these objects may represent a younger phase in a neutron star's life cycle. The powerful magnetic processes within magnetars are thought to significantly influence their evolution, continuing to shape their development long after the star has exhausted its nuclear fuel. Furthermore, magnetars do not exist in isolation. Their presence can have profound effects on their environment, influencing nearby stars, gas clouds, and interstellar matter. The intense radiation and magnetic forces exerted by a magnetar can cause fascinating changes in the surrounding cosmic material, altering the behavior of other stars and interstellar gas. As scientists continue to study these remarkable objects, new theories about the final stages of stellar life emerge. Magnetars not only help to refine our understanding of how massive stars meet their end, but also highlight how unique and extreme factors, like magnetic fields, can lead to vastly different outcomes in the universe. These discoveries have profound implications for how we think about the life cycles of stars and the cosmos at large. The study of magnetars enriches our understanding of how various factors, such as a star's mass, rotation speed, and magnetic properties, influence its destiny and the fate of the surrounding universe. The more we learn about these extraordinary objects, the more we realize how deeply interconnected the forces of nature are, shaping everything from the birth of stars to the most violent events in the cosmos. Magnetars serve as cosmic laboratories where extreme physics are on full display. Their magnetic fields, which are billions of times stronger than those found in typical magnets on Earth, provide an unprecedented opportunity to study the behavior of matter under conditions that simply cannot be replicated on our planet. One of the great mysteries that magnetars help to unravel is the nature of matter under immense pressures and densities. The core of a magnetar is so compact that it is essentially a soup of neutrons, and understanding how material behaves in such a state offers profound insights into the fundamental forces that govern the universe. Another remarkable feature of magnetars is their explosive bursts of energy, detected as soft gamma ray repeats. Each burst of radiation offers a glimpse into the complex processes occurring within these stars. By analyzing these bursts, scientists can uncover important details about the dynamics of stellar evolution, as well as gain new insights into the origins of supernova explosions. Magnetars are also linked to the phenomenon of gravitational waves, ripples in spacetime caused by the motion of massive objects. Observing events associated with magnetars could further refine our understanding of these waves, contributing to the burgeoning field of gravitational wave astronomy. The study of magnetars thus bridges many key concepts in astrophysics, from the behavior of matter in extreme environments to the energetic processes that drive some of the most violent events in the universe. Each new discovery related to these mysterious objects not only enhances our understanding of how stars evolve and die, but also sheds light on the fundamental laws of nature, unlocking new possibilities for future research. Pulsars, another fascinating type of neutron star, stand out due to their exceptional behavior. To understand why pulsars are so unique, it is important to first grasp the nature of a neutron star itself. When a massive star reaches the end of its life and undergoes a supernova explosion, the core of the star collapses under the force of gravity, becoming incredibly dense. This collapse leads to the formation of a neutron star composed almost entirely of neutrons packed together in an extraordinarily compact space. What distinguishes pulsars from other neutron stars is their rapid rotation and the strong magnetic fields that accompany them. As a neutron star spins, it generates a magnetic field through the motion of charged particles within it. In pulsars, however, the magnetic field is tilted relative to the star's rotation axis, creating an interesting and dynamic interaction between the star's magnetic field and its rotation. This misalignment leads to the emission of beams of radiation, similar to the beams of a lighthouse from the star's magnetic poles. These beams sweep through space, and if they pass near Earth, we detect them as periodic pulses of radiation. This is why pulsars are called pulsating stars, because their emission pattern creates a regular rhythm of pulses. Some pulsars spin incredibly fast, rotating hundreds of times per second, producing a consistent and observable pattern across vast distances. Not all neutron stars exhibit this behavior. Many do not rotate at such high speeds, nor do they have the necessary alignment of their magnetic fields to produce regular pulses. Therefore, pulsars represent a distinct subset of neutron stars. Their unique properties make them incredibly valuable for astronomers, as their predictable and regular pulses allow researchers to use them as highly accurate cosmic clocks. These pulsars provide a precise tool for exploring the structure of space-time and testing theories in physics, including Einstein's theory of general relativity. The discovery of pulsars marked a monumental moment in the history of astrophysics. In the late 1960s, a young British astronomer named Jocelyn Bell Burnell was analyzing data from a large radio telescope as part of her doctoral research. While studying radio waves collected from the sky, she noticed a series of regular, periodic signals. These signals appeared almost like a cosmic ticking clock, occurring at precise intervals, which initially led Bell Burnell and her colleagues to wonder if they had detected signals from extraterrestrial civilizations. The signals were even given the playful nickname Little Green Men, LGM. However, as more of these signals were detected, it became clear that they were not of artificial origin. Instead, these pulsations were linked to a previously unknown type of celestial object, pulsars. The identification of pulsars represented a breakthrough in our understanding of the universe. They are rapidly rotating neutron stars that emit beams of radiation which sweep across space. When these beams cross Earth's path, we detect the periodic pulses of radiation. The discovery of pulsars opened up a new field of study, providing critical insights into the life cycles of stars, the behavior of matter in extreme conditions, and the dynamics of gravity and space-time. Beyond their scientific significance, pulsars also became indispensable tools for testing theories in physics. Their regular pulses serve as a natural laboratory, allowing scientists to confirm predictions about general relativity and investigate the nature of space-time. The discovery of pulsars marked a significant leap forward in our exploration of the cosmos, offering a glimpse into the complex and fascinating processes that govern the life and death of stars. As we continue to study pulsars, magnetars, and other exotic objects in space, we move ever closer to unlocking the deepest secrets of the universe. Furthermore, the precise intervals between the pulses of these extraordinary cosmic objects provide scientists with an unparalleled opportunity to explore the vast expanse of the universe. By observing these signals, we can begin to measure the immense distances between us and distant stars and even detect the subtle ripples in the fabric of spacetime known as gravitational waves. The discovery of pulsars has marked a profound shift in our understanding of astrophysics, opening the door to an entirely new realm of phenomena and revealing the intricate, complex nature of the universe itself. Pulsars are not merely interesting anomalies. They are cosmic beacons, serving as critical tools in unraveling the mysteries of the cosmos and its fundamental laws. Pulsars are neutron stars, which are the remnants of massive stars that have exploded in supernova. These highly magnetized, rapidly rotating stars emit intense beams of radiation that sweep across space in a precise, regular rhythm. To an observer on Earth, these emissions appear as periodic pulses, like the ticking of a cosmic clock. The precision of these pulses is remarkable, and it is this regularity that makes pulsars invaluable for a wide range of scientific investigations. As these pulses spin and their beams sweep through the vastness of space, if Earth happens to lie in the path of one of these beams, we observe a rhythmic signal that can be timed with extraordinary accuracy. This consistency in timing allows scientists to probe many different aspects of the universe, from the nature of gravity itself to the behavior of matter under the most extreme conditions imaginable. One of the most intriguing ways in which pulsars have transformed scientific inquiry is in their ability to test the principles of Einstein's general theory of relativity. For instance, the regular timing of pulsar signals provides an opportunity to study how gravity influences light and the flow of time, especially when pulsars are part of binary star systems, systems where two stars orbit one another. In these systems, the gravitational pull of one star affects the motion of the other, causing variations in the timing of the pulses we receive on Earth. These fluctuations in timing offer a unique way to study the effects of gravity in action, providing real-world evidence of the concepts Einstein first proposed in his theory. In addition to helping test Einstein's theories, pulsars are essential in the ongoing quest to understand the enigmatic nature of dark matter and the behavior of matter under extreme conditions. Neutron stars are incredibly dense, so much so that they can contain a mass greater than the Sun, all compressed into a sphere only a few kilometers in diameter. This remarkable density allows scientists to study the behavior of matter in a state of extreme compression, providing crucial insights into the equations that govern matter in these conditions. By studying pulsars, we can push the boundaries of physics, exploring regions of the universe that were previously inaccessible to direct observation. One of the most groundbreaking applications of pulsar research is their potential to detect gravitational waves. These waves are tiny ripples in the fabric of space-time generated by the movement of massive objects like merging black holes or neutron stars. By observing the tiny, precise changes in the timing of pulsar signals caused by the distortion of space-time as gravitational waves pass through, the scientific community hopes to directly observe these elusive waves. Detecting gravitational waves could provide new insights into the most violent and energetic processes taking place in the universe, offering an entirely new way of observing the cosmos. Pulsars are not merely fascinating objects in their own right. They are also invaluable tools in the ongoing exploration of the universe. By offering a unique window into the behavior of gravity, extreme matter, and even the most distant cosmic events, pulsars help astronomers piece together the grand puzzle of the universe. They serve as natural laboratories for testing the laws of physics in environments that cannot be replicated here on Earth. Binary pulsar systems in particular present an extraordinary opportunity to investigate the fundamental nature of gravity in ways that are not possible with other celestial objects. In these systems, two neutron stars orbit around each other, with one emitting regular pulses of radiation. As these stars move through their orbits, the changing distance between them and the Earth causes subtle variations in the timing of the pulsar signals. These tiny variations in timing can be measured with remarkable precision, offering a detailed record of how gravity affects the motion of these massive objects. Scientists can observe the interactions between the two stars in real time, providing a valuable test of Einstein's laws of gravity. Perhaps one of the most significant discoveries to come from the study of binary pulsar systems is the direct confirmation of gravitational waves. As the two neutron stars spiral toward each other, they emit gravitational waves, ripples in space-time that carry energy away from the system. By carefully measuring the timing of pulsar signals, scientists have confirmed predictions made by general relativity about how these waves cause the stars to gradually move closer together over time. This discovery not only validates Einstein's theory, but also opens the door to further investigations into the nature of gravitational waves and their role in shaping the universe. Moreover, binary pulsar systems offer a unique opportunity to study the effects of intense gravitational fields on the passage of time itself. In such extreme environments, time flows more slowly, a phenomenon known as time dilation. By measuring how time flows for the pulsar in relation to its companion star, researchers can deepen their understanding of gravity under extreme conditions. These systems serve as natural laboratories, offering empirical evidence that can either support or challenge our current theories of gravity and space-time. In addition to their role in advancing our understanding of gravitational physics, pulsars also continue to fascinate researchers because of their potential to provide critical insights into other areas of science. One area of intense interest is the study of pulsar emissions, particularly the mechanisms behind their rhythmic signals. By observing these emissions with advanced telescopes, scientists are able to glean valuable information about the pulsar's magnetic fields and rotation speeds. These observations offer important clues about the violent processes that lead to the formation of these extraordinary stars. Furthermore, pulsars are being studied as a tool for investigating the fundamental laws of physics. Scientists are exploring how pulsars can help test theories of gravity, particularly in the extreme environments found within neutron stars. Pulsars are also being used in array systems to detect gravitational waves, ripples in space-time caused by massive celestial events. This method has the potential to open up a new window into some of the most energetic and mysterious phenomena in the universe. Another promising area of pulsar research is their ability to probe the interstellar medium. As pulsar signals travel vast distances through space, they can be affected by the material between the pulsar and Earth. By studying the changes in these signals, scientists can learn more about the composition, density, and distribution of this interstellar matter. This research provides an invaluable tool for understanding the structure and behavior of the universe at large, as well as the forces that shape its evolution. Through the study of pulsars, scientists are not only gaining deeper insights into the nature of gravity, time, and matter, but they are also unlocking new ways to explore the universe's most profound mysteries. Pulsars are serving as the cornerstone of a new era in astrophysical research, allowing us to peer deeper into the cosmos than ever before. With each discovery, we move closer to understanding the very fabric of our universe, one pulsar at a time. Investigations are underway into the enigmatic millisecond pulses produced by ultra-fast spinning stars. These fascinating cosmic objects, which rotate at incredible speeds, offer profound insights into the behavior of matter under the most extreme conditions found in the universe. By studying the environments surrounding these stars, researchers are piecing together crucial information that could reveal more about the dynamics of binary systems, where two stars orbit one another in a delicate dance. Moreover, this research could potentially lead to groundbreaking discoveries regarding exotic states of matter that challenge our understanding of the physical world. The exploration of these pulses is multifaceted, spanning several scientific disciplines, including astrophysics, fundamental physics, and cosmology. The ultimate goal is to unravel the mysteries of the universe by closely examining these remarkable cosmic beacons that shed light on the very fabric of space and time. Quantum cosmology, a rapidly evolving field of scientific inquiry, is dedicated to understanding the universe at its very beginning by combining the principles of quantum physics and general relativity. Quantum physics, at its core, suggests that particles can exhibit strange and counterintuitive behaviors, existing in multiple states simultaneously and defying classical rules of motion. In contrast, general relativity offers a grand picture of the universe, explaining how massive objects like planets and galaxies bend the fabric of space and time through their gravitational influence. The challenge, however, lies in reconciling these two theories as they operate in vastly different realms. While general relativity excels at describing large-scale phenomena, such as the warping of space-time, it struggles to account for the minuscule probabilistic behaviors that dominate at the atomic and subatomic levels. On the other hand, quantum mechanics effectively describes these small-scale interactions, but fails to provide a satisfactory explanation for large-scale gravitational effects. Quantum cosmology seeks to bridge this gap by unifying these two perspectives, particularly in events such as the Big Bang, where both quantum mechanics and gravity played a crucial role in shaping the universe's early development. Imagine trying to understand a complex dance where every movement impacts the next, a dynamic system governed by both the microcosmic and macrocosmic scales. In this context, researchers are exploring how the quantum behavior of particles at the birth of the universe may have influenced its early stages, and how this seemingly chaotic probabilistic nature can be reconciled with the smooth, predictable structures described by general relativity. By examining the universe's origins through this quantum lens, scientists hope to uncover fundamental insights into its formation, evolution, and the overarching laws that govern its behavior. This quest to unify our understanding of the universe's origins is not only a theoretical exercise, it holds the potential to answer some of the most profound questions about existence itself. Quantum cosmology provides an exciting new way to understand the creation of the universe, focusing on the incredibly small scales of particles and the behaviors dictated by the laws of quantum mechanics. Imagine, if you will, the universe emerging from an infinitesimally small point, where the very concepts of space and time as we know them did not exist. In this primordial state, the universe could be viewed as a superposition of endless possibilities, much like a coin spinning in the air, existing as both heads and tails simultaneously until it lands. Rather than a single moment of creation, the universe emerges from a complex, interconnected web of quantum fluctuations. These fluctuations create bubbles of space-time that expand and evolve, giving rise to distinct regions of the universe, each with its unique characteristics. This scenario gives rise to the idea of a multiverse, where our universe is just one of countless others, each governed by its own set of physical laws. One of the most profound implications of quantum cosmology is its potential to redefine our understanding of time itself. Traditionally, time is viewed as a linear progression, constantly moving forward from past to present to future. However, in the context of quantum cosmology, time may not have flowed in a conventional linear fashion during the universe's earliest moments. Instead, time could have behaved in a far more fluid and dynamic manner, allowing for the existence of multiple timelines and realities, each unfolding according to the interplay of quantum events. This perspective challenges our traditional views of the universe's birth, suggesting that the creation of the cosmos was not a simple explosion, but rather a much more complex and multifaceted process driven by the interactions of quantum forces. As we continue to delve into the mysteries of quantum cosmology, researchers are pushing the boundaries of our knowledge, attempting to synthesize the principles of quantum mechanics with the vast, gravitationally dominated structures of cosmology. However, the challenge of reconciling these two realms is not without its difficulties. Quantum mechanics, with its probabilistic and uncertain nature, operates at the smallest scales, describing how particles interact with each other in ways that defy intuition. On the other hand, cosmology concerns itself with the large-scale structure of the universe, where gravity dominates and classical physics reigns. This divergence in how these two theories operate creates a fundamental challenge in bridging the gap between them, particularly when we consider the singularity of the Big Bang, a point at which the laws of physics as we know them break down, making it nearly impossible to understand what truly happened at the universe's birth. The quest to merge quantum mechanics and cosmology into a single unified theory has spurred the development of various frameworks, such as string theory and loop quantum gravity. These theories aim to explain how both quantum and gravitational forces can coexist in a single framework, but they are far from conclusive. One of the greatest obstacles lies in the lack of experimental evidence to test these theories, as as we currently lack the technology to probe conditions that existed at the dawn of the universe. This challenge highlights the need for new methods of investigation, as well as the development of innovative tools that could allow us to observe phenomena on scales far beyond what is currently possible. As the search for a unified theory of quantum cosmology progresses, it raises more questions than it answers, inviting new ideas and approaches that could reshape our understanding of the universe's origins. This pursuit is not merely a theoretical exercise, it is a profound journey that pushes the limits of what we know and invites us to reconsider everything we thought we understood about the cosmos. The implications of these theories are far-reaching, potentially offering answers to the deepest questions about existence itself. One of the most intriguing aspects of quantum cosmology is its ability to reshape our perception of time and space. In traditional cosmology, space and time are treated as fixed and immutable entities, akin to a stage on which events unfold. Quantum cosmology, however, suggests that these elements may not be as solid and unchanging as we once believed. Instead, space and time are inextricably intertwined with the particles and fields that make up all matter and energy. They fluctuate and evolve in response to the behaviors of the tiniest particles, like creating a dynamic and ever-changing backdrop against which the universe's events play out. This perspective opens the door to new ways of thinking about time itself, no longer a constant, but a byproduct of deeper quantum-level interactions. In this framework, the passage of time may not be uniform across the universe. Rather, it could vary depending on the conditions present in different regions of space-time. Time, in this view, emerges from the interactions of particles and fields at the quantum level, meaning that it is not an independent entity, but a manifestation of more fundamental processes. This idea fundamentally challenges our traditional understanding of time, suggesting that it could be far more malleable and context-dependent than we have ever imagined. As quantum cosmology continues to evolve, it promises to offer an entirely new way of thinking about the universe, its origins, and the very nature of time and space itself. Quantum cosmology offers an entirely new perspective on the universe's origins and its future. It invites us to peer through a lens that blends the vast scope of cosmology with the peculiar and often mind-boggling behaviors of quantum mechanics. This fusion not only sheds light on the birth of the cosmos, but also raises profound questions about the nature of time itself, urging us to reconsider everything we think we know about beginnings, endings, and the flow of existence. In this context, the Big Bang, a defining moment in our understanding of the universe, may not have been a singular event as previously thought. Instead, it could have been a complex interaction of quantum fields, each one contributing to the birth of everything we know. As scientists continue to delve deeper into the intricate dance of quantum mechanics and cosmology, the very concept of origin begins to blur, revealing a universe much more dynamic and unpredictable than we could have ever imagined. The universe may not simply have started with a bang. It could be a continuously evolving system shaped by quantum fluctuations, where the boundaries of space and time themselves are malleable, influenced by the invisible forces that govern them. The implications of such discoveries could transform our understanding of the universe's ultimate fate, offering an exciting new framework for exploring the deepest questions of existence. Recent technological breakthroughs are accelerating progress in quantum cosmology, making it possible for scientists to examine these complex phenomena with greater precision and clarity than ever before. At the core of these advancements is quantum computing, an innovative field that is changing the way researchers approach seemingly insurmountable problems. Quantum computers can perform calculations at an extraordinary speed, processing complex models and simulations far faster than traditional computers. These tools allow cosmologists to simulate early universe conditions with remarkable accuracy, shedding new light on what the cosmos was like just moments after the Big Bang. With these powerful tools, scientists can now explore a universe that was once beyond our reach, unraveling the mysteries of the very forces that shaped the universe's birth. Moreover, we are witnessing dramatic improvements in observational technology that allow us to gather data from distant corners of the cosmos. Advanced telescopes and detectors now enable astronomers to measure the faintest signals, such as the cosmic microwave background radiation, an afterglow of the Big Bang that provides invaluable clues about the universe's early state. These innovations help researchers piece together the puzzle of the universe's origins using data that only a few years ago would have been impossible to obtain. As cosmologists study the intricate patterns in the background radiation, they gain insights into how the universe expanded and evolved, helping us refine our understanding of quantum cosmology itself. Another frontier in this exciting field lies in the realm of quantum gravity and string theory. These groundbreaking theories challenge traditional notions about the fabric of space-time, suggesting that what we perceive as the four dimensions of space and time may be just a small part of a much larger and more complex reality. These theories propose that space-time itself is woven from intricate quantum threads, and that at the most fundamental level, the universe is governed by principles we are only beginning to grasp. The interplay between these theories could lead to profound new interpretations of the universe, helping us decode the very mechanisms that drive cosmic events and the fundamental forces that shape reality. As these diverse strands of research come together, collaboration across disciplines becomes increasingly common. Physicists, mathematicians, and computer scientists are now working side by side, combining their unique skills to tackle the complex problems at the heart of quantum cosmology. This interdisciplinary approach fosters innovation, enabling scientists to break through long-standing barriers in the search for answers. With the combined power of cutting-edge technology, sophisticated computational tools, and groundbreaking theoretical models, the future of quantum cosmology looks promising. The next few decades could see a dramatic shift in our understanding of the universe, as we uncover secrets that will forever alter our perception of space, time, and reality itself. Quantum cosmology not only enhances our understanding of the universe's origins, but also challenges our very concept of reality. As scientists venture deeper into this uncharted territory, they may reveal new dimensions of existence, dimensions that lie beyond the limits of our current knowledge. These discoveries will likely reshape not just our understanding of the cosmos, but also the way we perceive our place in it. The deeper we explore, the more we realize that the universe is not a static, unchanging entity, but a dynamic, living system constantly in flux, driven by quantum forces beyond our comprehension. One of the most fascinating phenomena discovered through this lens is gravitational lensing, a process that occurs when a massive object, such as a galaxy or a black hole, distorts the light coming from a more distant object. This bending of light occurs due to the powerful gravitational pull of the massive object, which acts like a cosmic magnifying glass. The light passing near this object is bent and warped, creating multiple images of the same distant galaxy or even distorting its shape in bizarre and unexpected ways. This phenomenon can be likened to looking through a curved piece of glass. The light no longer travels in a straight line, but instead follows a new path shaped by the curvature of the glass. For astronomers, gravitational lensing is a game changer, offering a unique window into the farthest reaches of the universe. It enables them to study objects that would otherwise be too faint or distant to observe, providing valuable insights into the structure and composition of these far-off galaxies. But gravitational lensing is not just a tool for magnifying distant objects. It is also a powerful way to study the invisible components of the universe, like dark matter. This mysterious substance, which makes up most of the mass in the universe, but does not emit light, can be detected indirectly through its gravitational effects on light. By studying how light bends and distorts as it passes near massive objects, scientists can map out the locations and distribution of dark matter, revealing its hidden influence on the cosmos. This extraordinary phenomenon is also helping astronomers to explore the nature of dark energy, a mysterious force that is believed to be driving the accelerated expansion of the universe. Though dark energy remains largely elusive, its effects can be seen in the way distant galaxies appear to be speeding away from us. By analyzing the light from these galaxies, astronomers can infer how dark energy interacts with the fabric of space-time itself. Gravitational lensing thus provides a dual-purpose tool. Not only does it help us peer deeper into the universe's past, but it also illuminates the unseen forces that govern its present and future. In essence, gravitational lensing serves as a cosmic flashlight, illuminating areas of space where dark matter and dark energy reside. By carefully studying the way light behaves as it interacts with these massive objects, scientists are slowly piecing together the puzzle of the universe's unseen components. This remarkable effect is allowing researchers to create detailed maps of the distribution of dark matter, helping to unlock the mysteries of the cosmos one lens at a time. As our understanding of this phenomenon deepens, it may one day provide the key to answering some of the most profound questions in modern astrophysics. What is the true nature of dark matter? How does it influence the formation and behavior of galaxies, and what role does it play in the universe's ongoing expansion? Gravitational lensing is more than just a scientific tool. It is a gateway to exploring the deepest, most fundamental questions about the universe's structure and evolution. Gravitational lensing is a captivating and transformative phenomenon that provides a unique window into the farthest reaches of the universe. It occurs when light from distant objects, such as galaxies, quasars, or even stars, passes near a massive object like a galaxy or a galaxy cluster. The gravity from this massive object bends and magnifies the light, acting as a cosmic magnifying glass, allowing astronomers to observe objects that would otherwise be too faint or distant to study in detail. This bending of light is not just a fascinating effect, but an invaluable tool in understanding the structure and evolution of the cosmos. The power of gravitational lensing lies in its ability to allow scientists to study the formation and evolution of galaxies by examining how light is distorted around large galaxy clusters. These massive structures grow and evolve over time, and the light bending caused by their gravity acts as a snapshot of the universe at different stages in its development. Through this, astronomers can trace back the history of the universe, exploring how galaxies and other cosmic structures have changed over billions of years. Each lensing event serves as a natural experiment, offering insights into the fundamental processes that govern the cosmos. Beyond studying galaxies, gravitational lensing is also crucial for observing exoplanets, distant worlds beyond our own solar system. When a star and its orbiting planet align with a background star, the gravitational pull of the planet causes a temporary brightening of the background star. This effect, called gravitational microlensing, allows scientists to detect exoplanets that would otherwise be too far or faint to observe. By studying these temporary changes in brightness, astronomers can not only confirm the existence of these distant worlds, but also gain deeper insights into planetary formation and the diversity of celestial bodies scattered across the universe. Gravitational lensing serves as a powerful method for shedding light on the most elusive and mysterious aspects of the universe, particularly dark matter and dark energy. Although dark matter cannot be directly observed, its presence can be inferred by examining how it influences the light paths of objects behind it. The distortions caused by gravitational lensing offer clues about the mass and distribution of dark matter in galaxies and galaxy clusters, helping scientists map out this unseen component of the universe. Similarly, gravitational lensing provides indirect insights into dark energy, the mysterious force responsible for the accelerating expansion of the universe. This phenomenon also allows scientists to probe the early universe. Light from the most distant quasars has traveled billions of years to reach Earth, and as it moves through space, it encounters various gravitational fields. These interactions create a layered understanding of the universe's structure and evolution. By studying these distant, ancient light sources, scientists can trace back to the very origins of the cosmos, gaining new perspectives on its birth and early development. Each instance of gravitational lensing opens up a new chapter in our understanding of the universe. This natural optical effect not only provides clearer images of distant celestial objects, but also reveals the intricate details of the lensing objects themselves. By analyzing how light is bent and distorted, astronomers can study the distribution of visible matter, such as stars and gas, as well as invisible matter like dark matter. This allows scientists to learn more about the structure and mass of galaxies, which is crucial for understanding how they form and evolve over time. Moreover, gravitational lensing plays a vital role in refining our understanding of cosmic dynamics. For instance, by observing lensed images of distant supernova, scientists can measure their brightness and determine their distance from Earth. This information is crucial for determining the rate at which the universe is expanding, known as the Hubble constant. Accurate measurements of this rate help astronomers refine their models of cosmic expansion and improve our understanding of the universe's overall behavior. Gravitational lensing's ability to enhance our view of distant galaxies, quasars, and even the very fabric of space itself has revolutionized modern astronomy. By using massive objects as natural lenses, scientists have been able to study some of the most distant and faint objects in the universe with unprecedented clarity. This has led to groundbreaking discoveries about the nature of dark matter, the expansion of the universe, and the existence of exoplanets. Gravitational lensing continues to reshape our understanding of the cosmos, pushing the boundaries of what we know about the universe and our place within it. At the same time, the study of gravitational lensing offers a profound glimpse into the complexities of space itself. Each bending of light provides us with valuable data that contributes to our understanding of cosmic phenomena, whether it's revealing the hidden structures of dark matter or offering new insights into the birth and evolution of galaxies. As astronomical instruments improve and our ability to study distant objects becomes more advanced, the role of gravitational lensing will only continue to expand, providing new opportunities to explore the mysteries of the universe. In addition to its impact on astronomy, gravitational lensing also holds significant promise for future scientific exploration. One of its most exciting applications is its potential to aid in the search for extraterrestrial life. Humanity continues to look outward into the cosmos. Preparing for communication with alien civilizations involves both scientific rigor and creative thinking. Scientists are exploring a variety of methods for sending messages across vast distances in space, and radio waves, which have already been used for interstellar communication, are seen as one of the most effective ways to transmit signals. But communication is not just about technology, it's also about language. The challenge lies in creating a universal form of communication that can bridge the gap between humanity and extraterrestrial civilizations. Since we cannot assume that alien species share our languages or concepts of communication, scientists have proposed using mathematics as a universal language. Mathematical principles, such as prime numbers or basic geometric shapes, are often considered universal and might be recognized by any intelligent species. These simple yet profound patterns could serve as the foundation for establishing contact with alien civilizations. Once a communication method is selected, the next challenge is interpreting any response we might receive. Signals from extraterrestrial intelligence could take many forms: sound, light, or even coded messages, requiring careful analysis and decoding. Scientists are working to develop systems and technologies that can help us interpret these signals, preparing humanity for the possibility of making contact with alien civilizations. However, preparing for contact with extraterrestrial life is not just a matter of technology and science. It also involves cultural and psychological readiness. The possibility of encountering intelligent alien life could challenge our very understanding of life, consciousness, and our place in the universe. This preparation requires a global effort, with nations and communities coming together to explore the profound implications of such an encounter. Open-mindedness, collaboration, and a willingness to rethink fundamental concepts are essential in ensuring that humanity is ready for this groundbreaking moment in human history. Through the study of gravitational lensing and its various applications, scientists are not only deepening our understanding of the universe, but also preparing us for the next great leap in space exploration. Whether it's uncovering the mysteries of dark matter, studying the evolution of galaxies, or preparing for the potential discovery of extraterrestrial life, gravitational lensing is helping to reshape our view of the cosmos and our place in it. As our understanding of this powerful phenomenon continues to grow, so too will our ability to explore and understand the vast, complex universe in which we live. Moreover, ongoing efforts in the field of astrobiology are steadily enhancing our understanding of how life could develop in environments vastly different from our own. These efforts are expanding the boundaries of our expectations, allowing us to imagine how extraterrestrial civilizations might not only survive, but thrive under conditions unlike those found on Earth. This broadens our perception of the kinds of alien life forms that could exist, as well as the ways in which they might communicate. It challenges us to think beyond the familiar and prepares us for the extraordinary possibility that one day we may make contact with beings from beyond our planet. In this context, preparing ourselves for such a monumental event involves much more than just technological or scientific advancements. It also requires us to mentally and socially prepare for the unknown. The preparation for first contact, if it were to ever happen, goes beyond the practicalities of science and technology. It calls for a global effort to ensure that we communicate in ways that are respectful, thoughtful, and effective. Establishing a universal method of communication, one that transcends language and cultural barriers, is a critical step in fostering an understanding with an alien civilization. Mathematical principles, which are thought to be universal, could serve as a foundational basis for this language, offering a common ground for initial interaction. Beyond that, the creation of systems to decode any potential responses from extraterrestrials would be essential in interpreting their messages accurately and meaningfully. A collaborative global approach is necessary as humanity steps into the unknown. The involvement of international bodies, such as the United Nations, is key to ensuring that any response to a potential extraterrestrial signal is unified and thoughtful. The implications of first contact are not limited to one country, one continent, or one culture. They would affect all of humanity. Therefore, the protocols for interacting with alien life should emphasize cooperation and transparency, ensuring that no single nation or entity acts unilaterally. In the event of detecting a signal from an extraterrestrial civilization, scientists would first verify the signal's authenticity using multiple observatories to rule out terrestrial interference. Only then would the discovery be shared with the global scientific community, with careful consideration given to how such information is presented to the public. The guidelines established for responding to extraterrestrial intelligence also prioritize caution, transparency, and thoughtful deliberation. These protocols aim to ensure that any interaction with alien civilizations is respectful and considers the potential complexities of communicating with beings whose culture, biology, and technology could be vastly different from our own. Careful analysis, cooperation across borders, and a phased approach to engagement are essential to making first contact a meaningful and responsible experience. As much as we hope for a positive discovery, these protocols reflect a deep understanding of the potential risks and uncertainties associated with such a profound event. The discovery of extraterrestrial intelligence could revolutionize our understanding of biology, evolution, and the origins of life. It would force us to rethink what it means to be intelligent, to be conscious, and to be alive. The potential to uncover new forms of life, learn from their technologies, and gain insights into their cultures could provide humanity with breakthroughs we cannot yet imagine. For instance, an alien civilization might have developed technologies that allow them to harness energy in ways we have not yet discovered, perhaps even capturing the power of stars themselves. Their knowledge of biology might offer us new medicines or ways to combat diseases that have plagued humanity for centuries. But as much as these possibilities are exciting, they also carry significant risks. The most obvious concern is the potential for misunderstandings or conflicts arising from the vast differences between two civilizations with fundamentally different ways of thinking, living, and existing. These misunderstandings could lead to disastrous consequences, including potential biological contamination. Both Earth and the alien civilization might carry pathogens that could wreak havoc if they were exchanged inadvertently. These concerns underscore the uncertainties that come with exploration. The thrilling sense of discovery is balanced by the dangers that lie in uncharted territory. Ethically, the implications of interacting with extraterrestrial life go even deeper. If we were to make contact with an intelligent alien species, we would be faced with profound moral dilemmas. Do they have rights similar to those of sentient beings on Earth? Are we entitled to treat them as we would any other species? Or do we owe them special consideration due to their intelligence and autonomy? These questions would inevitably spark debates about exploitation and the potential manipulation of these beings for our own benefit. Humanity's history with colonialism casts a long shadow on these discussions, and the ethics of interaction would likely lead to difficult questions about power, control, and responsibility. Moreover, how the public and governments react to the discovery of extraterrestrial life is entirely uncertain. Would we come together as a species to celebrate the discovery of life beyond Earth, or would fear, paranoia, and mistrust take over? The idea of interacting with intelligent beings from another world raises the potential for societal upheaval. Our collective response to such a monumental event could reshape human civilization in profound ways, potentially either uniting or dividing us, depending on how we approach the situation. As we contemplate the possibility of making contact, we are forced to confront both our scientific curiosity and our moral responsibilities. While the prospect of learning from an advanced extraterrestrial civilization could drastically enhance our understanding of the universe, it also challenges us to confront the ethical implications of such an encounter. The unknown nature of the encounter presents an opportunity to grow, but also a warning that our curiosity must be tempered with caution, respect, and responsibility. The idea of collaborating with an alien civilization, of sharing knowledge, technologies, and wisdom could be transformative. Imagine the possibilities. A civilization with technological capabilities far beyond our own could open doors to innovations that are currently beyond our wildest imaginations. They might have unlocked energy sources that could revolutionize our ability to produce and consume power, perhaps even mastering energy harnessing on a stellar scale. They may have developed new materials that could fundamentally change the way we build, construct, and interact with the physical world. Such collaboration could lead to breakthroughs in medicine, allowing us to cure diseases that have plagued humanity for generations. And as we share knowledge about artificial intelligence, perhaps our own systems could evolve in ways that improve efficiency and performance far beyond what we can currently conceive. In such a partnership, we could expect to see cultural exchanges that challenge our traditional views on ethics, philosophy, and our place in the universe. A thriving collaboration with extraterrestrial intelligence could inspire new ways of thinking, driving a cultural renaissance that not only propels our technological advancements, but also fosters new perspectives on human existence. It is a world where our limitations as a species begin to dissolve, replaced by the vast expanse of shared progress. However, establishing and nurturing relationships with extraterrestrial civilizations presents unique challenges, particularly in communication. Language barriers and cultural differences will pose significant hurdles. Human languages, shaped by our own experiences, would likely be irrelevant to an alien civilization. Instead, we would need to explore fundamental forms of communication, such as mathematics, music, or visual representations, which may be more universal in nature. The sheer distances between stars would also complicate communication. Even if we were to detect an extraterrestrial signal, the time it would take for a message to travel across the vastness of space would mean that real-time communication would be impossible. The vastness of space, along with differing technological capabilities, also presents challenges in terms of mutual interest. An alien civilization might not even be aware of our existence, or they may view us as too primitive to warrant interaction. Furthermore, our history of mistrust, especially when it comes to first encounters, suggests that we must approach the situation with extreme caution. If an extraterrestrial civilization perceives us as a threat or as a potential source of conflict, the peaceful interaction we hope for could be jeopardized. The stakes are high, and the uncertainties that come with such an encounter are immense. But the potential for discovery and collaboration remains one of the most exciting frontiers humanity could ever explore. The prospect of interacting with alien life raises an array of ethical concerns that demand careful reflection. How do we approach the existence of beings from another world with the respect they deserve? How do we honor their autonomy, their culture, and their very right to exist without imposing our own values or causing unintended harm. Any form of interference, no matter how well-intentioned, could lead to consequences we cannot fully predict. The risk of destabilizing the delicate balance of their society, or worse, jeopardizing ours, looms large. These questions transcend the theoretical and touch upon the very heart of our moral compass as we look to the stars. At the same time, the rapid pace of technological advancements complicates this discussion further. As we continue to develop new tools and methods for making contact, we find ourselves at a crossroads. What methods of communication or exploration are responsible? What methods will respect the autonomy of extraterrestrial civilizations? These are not just scientific or technical questions, but ethical ones. The future of humanity in space, then, will require not only a commitment to exploration, but also to a deep and unwavering commitment to peace, respect, and understanding. It is only through this mindset that we may hope to forge bonds with other life forms in the universe, bonds that could lead to a more profound understanding of ourselves and the cosmos. Human space exploration has radically shifted the way we understand the universe and our place within it. When humans first journeyed beyond the Earth's atmosphere, the goal was simple yet profound: to escape the confines of our planet and explore the unknown. The adventure was as much about breaking free from earthly limits as it was about venturing into a new, uncharted realm. Over the decades, this pioneering spirit evolved into something far more sophisticated, an ambitious and ongoing investigation into the solar system and beyond. This quest has provided us with invaluable insights into the fundamental nature of space, time, and even the very essence of human existence. Astronauts who venture into space bring back more than just samples of celestial materials. They bring back knowledge that has changed the course of science and technology. In the weightlessness of space, experiments become possible that could never be replicated on Earth. Researchers have studied fluid dynamics, combustion, and even the properties of materials in ways that open new doors to scientific innovation. These experiments have not only expanded our understanding of the natural world, but also driven technological advances that have found practical applications in industries ranging from medicine to engineering. Perhaps the most groundbreaking contributions from human space exploration, however, are the discoveries we've made about other celestial bodies. Missions to the Moon and Mars have provided humanity with direct samples of lunar soil and Martian rock, unlocking secrets about the formation and geological history of these distant worlds. By analyzing these materials, scientists have been able to piece together a timeline of our solar system's evolution, giving us new insight into its age, its planetary dynamics, and the conditions that make life possible. Space telescopes like the Hubble Space Telescope have also revolutionized our understanding of the cosmos, allowing us to peer into distant galaxies and observe cosmic phenomena millions, even billions of years old. By capturing light that has traveled vast distances, Hubble and other telescopes have granted us a glimpse into the distant past, illuminating the early stages of star formation, the nature of black holes, and the cosmic forces that shape the universe. These discoveries, however, are not merely academic. They stir something deeper within us, a sense of wonder and awe that transcends the scientific data and connects us to something greater than ourselves. As we look into the infinite expanse of space, we are reminded that we are not simply inhabitants of Earth, but part of a much larger, interconnected universe. Each mission, each discovery, compels us to ask more profound questions. Is there life beyond our planet? What is our place in this vast, mysterious cosmos? And perhaps most importantly, what does the future hold for humanity in space? Human space exploration has turned abstract philosophical questions into tangible, practical investigations. From the molecular building blocks of life to the intricate, expansive architecture of the universe, every new discovery brings us closer to understanding the very essence of existence. Space telescopes and probes have dramatically expanded our knowledge, most notably through the confirmation of exoplanets, planets orbiting stars outside our solar system. Instruments on telescopes like the Kepler Space Telescope have identified thousands of these distant worlds, deepening our understanding of planetary systems and raising the tantalizing possibility that some of them might harbor conditions suitable for life. Perhaps even more astonishing was the detection of cosmic microwave background radiation, an afterglow of the Big Bang. This faint light, which has traveled across the universe for billions of years, offers a snapshot of the universe in its earliest moments, revealing crucial details about its formation and the conditions that allowed it to evolve into the universe we observe today. Space telescopes like Hubble have been instrumental in this discovery, enabling scientists to study the structure of galaxies and to gain a clearer understanding of the expansion of the universe itself. Space probes like Voyager have also sent back a treasure trove of data, expanding our understanding of the outer reaches of our solar system. These probes have traveled far beyond the orbits of the planets we know, delivering detailed information about Jupiter's intense weather systems and Saturn's stunning rings. They have helped us appreciate the sheer diversity of planetary systems and the unique features of each celestial body. And in recent years, the study of dark matter and dark energy has introduced a new transformative chapter in our exploration of the universe. Through observations made by telescopes, scientists have concluded that most of the cosmos is made up of materials that remain unseen, dark matter and dark energy. This revelation has fundamentally altered our understanding of the universe, encouraging a new era of inquiry into its mysterious expansion. As humanity continues to explore the cosmos, missions to the Moon, Mars, and other far-off destinations have revealed new layers of history and potential. Space probes and rovers, such as those sent to Mars, have provided unprecedented views of distant worlds. For example, the Mars rovers have unearthed evidence of a watery past on the red planet, suggesting the possibility of past life and setting the stage for future exploration that might one day uncover signs of microbial life on the planet. Every discovery builds upon the last, creating an ever-growing body of knowledge that not only informs us about other worlds, but also deepens our understanding of our own. International cooperation has played a pivotal role in expanding the frontiers of space exploration. When countries collaborate, they pool resources, expertise, and technology, forming a more robust and effective framework for scientific discovery. The International Space Station, ISS, stands as a testament to this kind of collaboration. By bringing together space agencies from around the world, the ISS has created a unique environment where astronauts and researchers can conduct experiments that would otherwise be impossible. These partnerships enable a diversity of approaches to scientific questions, as different cultural perspectives often lead to innovative breakthroughs. Beyond the scientific benefits, international collaboration in space also promotes peace and diplomacy. Working together on a shared goal, the exploration of space, nations can build trust and forge friendships that extend beyond the realm of science. This shared interest provides a platform for dialogue, allowing countries to address global issues and work together towards solutions that benefit all of humanity. Additionally, by pooling their financial resources, countries can undertake ambitious projects that would be far too costly for any single nation to accomplish on its own. This approach has made it possible to explore distant planets, search for extraterrestrial life, and embark on missions that were once thought to be beyond our reach. One of the most exciting missions currently on the horizon involves the study of the cosmic microwave background, the faint radiation left over from the Big Bang. This mission seeks to analyze this ancient light to gain insight into the conditions that existed immediately after the universe's birth. By examining this primordial radiation, scientists hope to uncover more about the elusive concepts of dark matter and dark energy, mysterious forces that constitute much of the universe but remain poorly understood. Another key mission involves the exploration of the outer planets and their moons, particularly those that may harbor the conditions necessary for life. Some of Jupiter and Saturn's icy moons are believed to contain subsurface oceans beneath their frozen crusts. Missions to these moons will search for signs of chemical activity that could indicate the presence of life beyond Earth. As humanity's gaze turns outward, the hope is to continue pushing the boundaries of exploration, not just for scientific knowledge, but for a deeper understanding of who we are and where we fit into the cosmic story. Through collaboration, exploration, and an unwavering curiosity, we are charting a path toward a future that is as boundless as the stars themselves. As humanity looks toward the stars, a new era of exploration is dawning, one that will reshape our understanding of the cosmos and perhaps even our place within it. Telescopes specifically designed to observe exoplanets, planets that exist beyond our solar system, are being developed and launched with an intensity never before seen in the history of space exploration. These cutting-edge instruments are not just about capturing stunning images of distant worlds. They are aimed at something far more profound, revealing the very secrets of life beyond Earth. By analyzing the atmospheres of these far-off planets, scientists hope to uncover vital clues about their composition, what they are made of, and whether they could harbor life. The stakes are high. Some of these telescopes will employ advanced technologies capable of detecting faint traces of light from exoplanets. These tiny, often invisible signals may reveal the presence of elements like oxygen and methane, molecules that, on Earth, are strongly associated with biological activity. The very search for these elements, coupled with other indicators, could allow scientists to determine if these distant planets might support life, or perhaps even host civilizations. It is an extraordinary endeavor, one that blends astronomical surveys, planetary exploration, and state-of-the-art observational tools. This ambition to explore the far reaches of the universe brings us to a fundamental question. Are we alone? Will we ever find evidence of life beyond Earth? The missions we are about to undertake will encompass a range of efforts, from the most sweeping, large-scale astronomical surveys to detailed planetary studies, and will rely on the latest technological breakthroughs. The pursuit of these questions will stretch our capabilities to the limit and, in the process, push the boundaries of human achievement. The search for answers to these questions is more than just a scientific undertaking. It is a journey that has captured the collective imagination of humanity for millennia. From the earliest days of civilization, when people first gazed up at the night sky, the stars were more than just distant lights. They were the keys to understanding the universe and our place within it. Cultures around the world wove stories and myths around the movements of celestial bodies, giving names and meanings to constellations, planets, and stars. These stories reflected the beliefs, fears, and aspirations of the societies that created them. They were the first attempts at comprehending the vastness of the cosmos and humanity's relationship with it. As our scientific knowledge of the universe has expanded, these myths and interpretations have evolved. The search for answers in the night sky has moved from the realm of speculation to the domain of rigorous observation and discovery. With the advent of powerful telescopes and space missions, we are now able to look farther and deeper into the universe than ever before. New discoveries, such as the identification of thousands of exoplanets, challenge us to reconsider our place in the universe and, perhaps, to entertain the possibility that life might exist elsewhere, waiting to be discovered. These discoveries spark not only wonder, but also raise new questions. The more we learn, the more we realize how much we still don't know. As scientists, we are forced to refine our understanding of the universe continually. This quest for knowledge is not a solitary endeavor. It is a collective human effort that spans disciplines and borders. Physicists, astronomers, mathematicians, engineers, and even artists collaborate to push the frontiers of exploration. Through their combined efforts, begin to see the universe not as an abstract, distant entity, but as something much closer to our hearts. Each new discovery encourages us to ask deeper questions about existence, consciousness, and our place in the cosmos. The importance of this work goes beyond the search for life or new worlds. It is about the process of discovery itself and the way it unites us as a species. The excitement surrounding missions to Mars, the exploration of black holes, or the study of exoplanets transcends national borders and individual interests. It reminds us that we share a common heritage and a common destiny. These missions are not just scientific projects, they're human endeavors driven by a collective desire to understand the universe and, by extension, ourselves. In many ways, these missions also embody the power of human curiosity and the drive to push beyond the known. The very act of exploring the unknown, the desire to understand what lies beyond the horizon, has been a defining characteristic of our species for centuries. From the first explorers who charted the Earth's continents to the pioneers of the space age who set foot on the moon, humanity has always been driven by a thirst for discovery. As we look to the stars, that same thirst compels us to explore the depths of space, to reach beyond the boundaries of our solar system, and to uncover the hidden truths that lie in the farthest corners of the universe. Ultimately, these endeavors do more than answer scientific questions. They influence culture, inspire innovation, and redefine what it means to be human. The questions we ask today about the universe reflect not only our scientific curiosity, but also our deeper need for meaning. The search for life beyond Earth, the exploration of distant stars and planets, and the study of cosmic phenomena invite us to imagine a future that transcends the limitations of our current understanding. These explorations broaden our perspective, enrich our cultural narratives, and challenge us to think in new ways. As we continue to explore the mysteries of the universe, we are reminded that the pursuit of knowledge is not just an intellectual exercise, but a fundamental part of what it means to be human. Our curiosity drives us forward, and as we reach for the stars, we are reminded that the quest for answers is a journey without end, a journey that will continue to inspire generations to come, uniting us in our shared pursuit of knowledge, discovery, and wonder.